Okay, so welcome to the second week of the workshop. We're gonna switch gears a little bit in the sense that so far we've only talked about LTE spectral lines mostly. We've assumed that the spectral lines we are considering form deep enough in the atmosphere that the source function is really determined by the local conditions, the temperature only, in fact. We've mentioned in passing that when we wrote down the formal solution in integral form, that this is not in general a closed equation, that the source function may depend on intensity, and not only the intensity in the line that you are considering, but also in different parts of the atomic model that you are considering. So now, today, this morning, we will look a little bit more formal at that problem, where the source function is depending on the temperature. And the reason it's not only dependent on the temperature, but also starts to depend on the radiation field. And typically this happens when scattering becomes important. So deeper in the atmosphere, there are enough collisions to maintain the Boltzmann levels in the atom. So again, the population numbers are only determined by the temperature, the local temperature. But when you go higher up in the atmosphere, collisions, density falls off, collisions are less frequent, and then the excitation and de-excitation by photons becomes important. And when you have that, the radiation field starts to determine the source function, and the radiation field can come from a very different place in the atmosphere than typically the collisions that determine the populations. And therefore the name non-local thermodynamic equilibrium, because the information that you have that determines the population numbers tends to be regulated by the radiation field, and the radiation field may come from a very different place in the atmosphere than the location that you are considering. Works? No, so the clicker doesn't. I can use the keyboard, but the okay, now it does. Okay, thanks. So a short overview of what we're going to talk about. First, I'll talk a little bit about when do we have non-LTE radiative transfer? How do we recognize it? What is the consequence for it that in the spectral lines that we see? In particular, I'll discuss some of the main chromospheric diagnostics that we have, the calcium 8542 line and the H-alpha line. In this presentation and in general, chromospheric line formation and non-LTE line formation are used alternatively, almost meaning the same thing, because the assumption is that lines that have enough opacity, that they are sensitive to the conditions in the chromosphere, necessarily form under non-LTE conditions. So when you talk about chromospheric lines, we typically talk about lines that form under non-local thermodynamic conditions in general. Then we'll briefly go over what we actually mean with local thermodynamic equilibrium. We'll write down the transfer equation with scattering. So far, when we wrote down the transfer equation, we had an absorption and emission coefficient. But in this case, we will now explicitly write the emission coefficient as a function of the radiation field, which is the case when you have scattering. Then we'll go to spectral line transfer. We will write down the equations and see how scattering, in fact, is a result of having a combination of absorption and emission and scattering. We'll look at the two-level atom as a scattering problem and go through the equations and show where exactly the problems are when we then want to solve the radiative transfer equation when scattering is present. That gives you a unique problem. Then we will write down for a more general case the multi-level transfer equations, and I'll give you some conclusions. So perhaps the case where the presence of the chromosphere is most evident is during a solar eclipse, when the moon blocks the very bright solar disk, the photosphere, and shows you only the very thin layer that is much hotter, but is also emitting mostly in the radiation of one spectral line, namely H alpha. Actually, this is a combination of H alpha and H beta, and that's why the color is so pretty. So this indicates that higher up in the solar atmosphere, something particular is going on. It's not the same situation as in the photosphere. This is another nice picture and the color in the colors. So when we talk about the chromosphere, we really talk about a layer that is considerably higher by 1,000 or 2,000 kilometers in the solar atmosphere. In this plot, as a function of horizontal position, there are several curves, and one of them is the optical depth unity and the continuum somewhere. Well, maybe it's not clear here. There's also here in the dotted line the location of beta equal 1, where beta is the ratio of the gas pressure over the magnetic pressure. So everything that's below this curve, curve of beta equal 1, is mostly dominated by gas pressure, by the dynamics of convection. Anything above that, the magnetic field, beta becomes less than 1. Actually, yes, becomes less than 1. No, larger than 1. Sorry, I'm always confused, because beta is a very strange convention in that it's the magnetic pressure over the gas pressure. No, the other way around. Yeah, exactly. That's the problem. Because it doesn't make sense, because when the magnetic pressure goes to 0, it goes to infinity, right? So it's kind of an odd unit quantity, and that's why it always confuses me. So when really the magnetic field starts to dominate, the structure of the atmosphere really changes a lot. It becomes much more filamentary. We've seen the movie that I showed you in the beginning last week, where when you change from the images in the blue, which were imaging the solar photosphere in the G band, and changing then to the orange light that was representative of line formation in the calcium H and K, you see that it changes from a convective structure to a magnetically dominated structure with filaments and a lot of different structure. And so some of the lines that we will consider form in this layer. One of them is calcium H, the other one calcium 8542. You see that it has optical depth unity at about 1,500 kilometers in the atmosphere. There's these shaded area is the opacity, or the opacity due to the helium 10830 line, which is a very particular case. Ivan will talk about it a lot when we talk about Hazel. That is it's a spectral line that really is populated by a very particular mechanism, and we'll talk about a little bit later in the next few days. But it is also sensitive to these layers. And then at the very top of the atmosphere, you have sensitivity in the line core of the magnesium H and K, which is visible in the iris spectra. So these are chromospheric lines, and they're also non-LTE lines because of the mechanism that I told you about in the beginning. As I told you, the structure of the solar atmosphere looks very different in these lines, because it samples, they typically sample much higher layers of the atmosphere. You see this really clear filamentary structure. You see layers where it looks like you almost look through the line, and this is actually the case. You can show that the opacity in the line there is such that you see more deep layers that are almost photospheric. In the sunspot, the situation is also different, because there the field is mostly vertical. so you don't see these filamentary structures as much. You see brightness variations along, and these brightness variations are not necessarily temperature related. They are, because this is an image at a given wavelength, some of this information that you see in brightness variations is Doppler shift, because the H-alpha lines are so steep that you move it a little bit, the intensity at one wavelength changes a lot. And some of this is actually variations in formation height that is mostly due to density rather than source function variation. So there's a lot to understand if we want to learn from an image like this. This is another image taken by Kevin with IBIS at the DST, our previous main high-resolution telescope in Sunspot in New Mexico. This is a comparison to clearly show you the difference between the photosphere, where you see the granulation, and an image in the core of 8542, where you really see very clearly the chromosphere. You can recognize some places, but all the other places would be very hard to see. Well, if the chromosphere looks like it, the photosphere looks like that. You would really have to look at very high spatial detail to understand, to recognize that. Now, do you all know what the G band is? Yes. Yes, it's a band at 430 nanometers that initially, when Fraunhofer looked at his spectra, looked like just one line, one broad line, and that's why he gave it the designation, the G in his designation. But it is a combination of a lot of CH molecular lines. And because it's so far in the blue, and because these molecular lines are very sensitive to temperature, you very neatly see very small scale magnetic fields. You very neatly see as bright points. It's difficult to see at this spatial scale because this is such a large field of view, but the G band is really particularly used to image these small scale bright features. This is a comparison with between 8542 and H-alpha image. This is an image that is actually a mosaic of 9, was it, Jana? 9 different fields of view combined. The seeing was good enough for a long period of time, so that Kevin was able to image these 9 locations and stitch them together in this beautiful image. So even though both 8542 and H-alpha are formed in the chromosphere, the images look very different, right? You can recognize similar locations, but there's much more filamentary structure in H-alpha. There's less so in 8542. There's more of these areas where it seems like you look through the chromosphere, where you see more photospheric layers. There's especially in these more quiet areas, there's less of this filamentary structure. So these lines are both in the chromosphere, but have very different sensitivities. So we can learn different things from them. Ideally, you would, in the same information, try to combine diagnostics like that, so that you have the most possible information that you can get from an observation, because each of these lines tells you different things. And if you combine them, you can learn better what are the conditions. Again, so going from the photosphere to, say, temperature minimum, to chromospheric line, to corona, once you do all these observations simultaneously, and hopefully your instruments will allow that, or semi-simultaneously, or even combining different instruments. Obviously, this is in the ultraviolet, so it's from space. So you'll have to find images taken from space at the same time as you do your observation. And combining those, you can trace the connectivity of the magnetic field and how the temperature connects, and how the structure really in a 3D fashion is, by looking at all these lines at the same time. Again, 2 images that at different wavelengths from the same time, that clearly show the difference in structure between the photosphere and the chromosphere. So, for instance, towards the limb, it's a little bit easier to see these small-scale bright features. We call them faculae when you see them like this. And when you then look at an H-alpha image, you see that there's magnetic field there that causes these bright points. So here are the spectral regions that have the main ionized calcium lines. We'll talk a little bit more why these calcium lines are so prominent. Calcium is one of the most abundant elements, and all calcium is in almost all calcium in the solar atmosphere is in its first ionized state. And this means that really the opacity in calcium lines is as big as it gets. These are the calcium H and K lines, are the strongest lines in the visible part of the solar spectrum. And these are three more lines. We'll show a little bit later how they are exactly connected. But this is just to give you a flavor of the spectrum as it looks like. This is then the H-alpha line compared to the 8542 line of calcium over the same range of wavelengths. So you get an idea of the broadening of the difference in broadening of the line, even though the line strength is very similar, as you can see, the depth of the line. So why would the calcium line be so much less broad than the H-alpha line? Exactly, yeah. So H-alpha is of course, hydrogen is the lightest element, so it has by far the largest thermal broadening. Even though the thermal broadening goes with the square root of temperature, the mass of calcium is 43 times that of hydrogen. So you have a significant additional thermal broadening in hydrogen lines compared to calcium lines. Let us briefly talk about a term diagram. You probably have all seen this, but these are the energy levels of hydrogen, of the hydrogen atom, the first 6 energy levels. And you see the ground level is at 0 in this diagram. And then the first excited level is at 10 electron volts. This is a big energy step. This typically about every 1 electron volt represents 10,000 Kelvin in temperature. So to excite this very back of the envelope, this 10 electron volts would require 100,000 Kelvin plasma. And there's not many places in the solar atmosphere where you have that's such high temperature. And this is actually very important because the H-alpha line, the lower level of the H-alpha line is this level. And so if you don't have high temperatures, it's very difficult to populate the ground level of H-alpha. And as you know, probably the opacity in the H-alpha is proportional to the population numbers in this lower level of H-alpha, right? So if you don't have a way to excite hydrogen from the ground level to the first excited level, you don't have opacity in H-alpha. And actually this is, we will get to that a little bit later. This gives some very specific formation characteristics of the H-alpha line. So these lines from the ground level to these different excited levels are the Lyman series, Lyman alpha, Lyman beta, Lyman gamma. And then we have the Balmer series, H alpha, H beta, which is also, both of those are in some way or fashion observable by the VPI, the imaging instrument in the DKIST. And then you have Gaussian, right? Gaussian, and then oops, bracket, but I haven't put those lines in. Right, so these are the different series of hydrogen lines. So calcium, I will show you a little bit later, is very similarly a fairly simple term diagram. Sometimes, however, and this is the case of magnesium 1, if we want to calculate the properties of, for instance, these lines, the magnesium B lines, which are also chromospheric lines, we have to account for many more atomic levels, because there are processes that will ionize magnesium, and then recombination will occur preferentially by de-excitation of all these higher levels. So to properly calculate the population numbers in this level, you have to calculate all the properties of all these spectral lines. Typically, if we would do this right, in a model atom, you have to account for about 60 or so magnesium 1 levels. So this is just to show you that when we do these non-LTE calculations, sometimes we can get away with only having a few lines and a few levels, like in the case of hydrogen or calcium, ionized calcium. But sometimes we do have to take into account many more radiative transitions. And again, the properties and the population numbers of these levels and lines may depend on the radiative transfer in all of these spectral lines. This is really, and we'll get to that a little bit later again, but this is really the problem and the interesting aspect of non-LTE radiative transfer. That the radiation field coming from a different location in any of these lines can affect the properties of this spectral line. Some of our instruments do full disk measurements of the magnetic field using chromospheric lines. In this case, the SOLIS instrument, which is at the moment still being installed after being moved from Kitt Peak to Big Bear, where it is now being installed. And hopefully in a few months, we'll be doing routine observations, synoptic observations, taking images every day so we can track the evolution of the magnetic field over the disk. These are images in the wing and the core of the 8542 line observed with the SOLIS instrument. And these are magnetic field derived from the core wavelengths, the Stokes V, and the wing wavelengths. So we have magnetic fields at two different layers by using the weak field approximation, where you match the derivative of Stokes I with Stokes V and derive the magnetic field in an approximation that's called the weak field approximation. Just to show you that indeed the intensity and also Stokes V of the 8542 line is indeed sensitive to chromospheric heights, 1000 to 1500 kilometers. This is a response function, like Carlos has showed last week. And this is the response function of Stokes I to the magnetic field. And you see that it is indeed sensitive, but also in a very complex way. It's not a straightforward way to use this response function to determine the magnetic field or the reaction of the Stokes profile to the changes in the magnetic field. Similarly, this is the response function of Stokes V to changes in the magnetic field. And so there it's a little bit more clear, but you see at the same wavelength, you do have positive and negative contributions. Yes.
So this is what you're showing is mostly the central part of the line, which is chromospheric. We know, like, while the extended wings have are formed in the photosphere. So that is the actual, that's scaled in the same way. So you have some sensitivity also in the wings.
Correct.
To the field.
Yes.
Correct. So the response function means that you are applying something, a disturbance in that part, wherever that.
So yes. So in every layer in the atmosphere, you apply a perturbation to the magnetic field, you calculate what the radiation field is from that perturbed atmosphere, and you subtract the unperturbed atmosphere from that. And when you write down the equations, you see that you can exactly represent the response function as a reaction of the atmosphere to perturbation of your quantity, in this case, the magnetic field. The reaction of the profile to the perturbations in that quantity at different heights in the atmosphere.
Okay, so here I would understand that the line is much more sensitive to perturbation of the field in the core.
Yes, and the reason is that when you have a Zeeman splitting, the different Zeeman components will actually move in wavelength slightly, and when you have a steep line wing, that you have larger sensitivity to those splittings.
Okay, thank you. Yes.
So that's the mechanical explanation, if you will.
All right, thank you.
And so Stokes V is similarly sensitive. You see that Stokes V compared to Stokes I has more sensitivity in the wings. So you can actually measure photospheric magnetic field by looking at Stokes V in the wing of these chromospheric lines, because the wings form deeper. But you see that even in this case, at the same wavelength, you have positive and negative contributions. So it will be difficult to see, to distinguish, for instance, between a positive change in the magnetic field and a positive change in V, or in deeper layer, or at a higher layer, a negative change of the magnetic field and a positive change in Stokes V. And you can explain this if you would look at the source function of this line, and you see what happens when the line slightly shifts because of Zeeman splitting. You can explain these kind of sensitivities, but that's a little bit beyond what we can talk about in the time of this presentation. So this is now the contribution function of H alpha to temperature changes, and you see that there's definitely sensitivity high up in the atmosphere. Oh, this is, I don't know why it's mirror flipped, but you see that H alpha is really sensitive to higher layers in these atmospheres. But there's an interesting case, right? You see that there's, in this region between about 400 and 800 kilometers, the response function has no values. This means that if you change the temperature in these layers, the H alpha line profile will not react to that, right? Because the response function has 0 values. And the reason for that is exactly what I told you right in the beginning, that the lower level of H alpha is the upper level of Lyman alpha. And it takes either radiation field that is pretty hot, or it takes electrons of about 100,000 Kelvin to excite hydrogen from the ground level to the first excited level, the upper level of Lyman alpha, the lower level of H alpha. And in the solar temperature minimum region, temperatures are only 4,000, 5,000 degrees, and there's not enough electrons, even in the tail of the Boltzmann distribution, that can excite hydrogen. So there's really almost no opacity in H alpha in these layers. And so it makes the sensitivity of H alpha kind of very peculiar, different than any other spectral line. This is the what did I plot then here? Oh, this is the contribution function. So the response function is actually very different. It's much more concentrated. The
previous figure was flipped.
Yeah.
Okay.
So yeah, but that doesn't matter. I mean, it's symmetric. So so but it's hard to read the yes. So here that you clearly, so for photospheric lines, if you look at it, the contribution function that David talked about a lot and the response function are very similar. If you plot them, the curves would look very similar. For chromospheric lines, this is not the same case because you see that in this case, the contribution or the response function is very more concentrated in one specific height. And this often has to do with sensitivity, not in the line itself, but in different lines. For instance, this could be exactly because of sensitivity in Lyman alpha. So if I raise the temperature, the intensity or the excitation in Lyman alpha goes up, and it changes the population numbers, and it changes the formation height of Lyman alpha, of H alpha. So, for instance, it could change the opacity of H alpha such that the line forms higher, and since that is the chromosphere, it forms at higher temperature. So you get a positive sensitivity of the H alpha line core intensity, but it's really due to the sensitivity of Lyman alpha excitation to the temperature rather than the source function of H alpha changing. That makes sense? So this is really one of the essences of non-LTE radiative transfer, that you have to worry not only about the properties of the line itself that you're considering, but also about the properties of how that line is connected with other energy levels in the atom that you're considering. And then this is the response function of the H alpha line to velocity. And you see that it has a very broad and deep sensitivity, and it's because the H alpha line wings are so steep. So you move the line a little bit, and the intensity at a given wavelength changes a lot. But it also shows you very clearly that H alpha line core images have such nice high contrast, because any velocity in the chromosphere will contribute to some kind of image shape, and typically these filaments that you see in H alpha are to a very large degree also the result of Doppler shifts rather than temperature or density variations. So I showed you these profiles before, but now let's ask the question. These are the calcium H and K lines, as I told you, the broadest lines in the solar optical part of the spectrum. This is the H alpha line on a similar, on the same wavelength scale. Maybe not the same wavelength scale, but comparable. So these lines are so much broader than H alpha, while there is how much more hydrogen than calcium? Does anyone know what the abundance of calcium is? Well, approximately, some guess. 10 to the minus, how much? Take a wild guess. No, it's more than that. Actually, much more than that. It's something, sometimes 10 to the minus 4. 6. No, you're right. Sorry. I was, yes, I remembered the 4, but so out of every hydrogen atom, right, or every calcium atom, there are almost 1 million more hydrogen atoms. Why you would expect that the opacity of hydrogen lines would be so much bigger than calcium lines, right? But the ionization potential of neutral calcium is only 6 electron volt, and as a result, in the solar atmosphere, you have mostly all calcium is in the singly ionized form. I think there's only up to about 10% at most of calcium that is neutral still. As I told you, the H alpha lower level is the upper level of Lyman alpha, and it lies at 10 electron volt above the ground level. The oscillator strength of H alpha and calcium K are similar. I mean, within an order of magnitude by a factor of 4, right? So you can imagine that the opacity in a spectral line is proportional to the oscillator strength. So actually there H alpha even wins. But if you remember that and we'll get to the exact expression later, the absorption coefficient contains the lower level population numbers, and for H alpha that is the upper level of Lyman alpha. So it has this e to the minus energy over kT, which is for Lyman alpha a big number. So the Boltzmann factor for the lower level of H alpha is very small, and so the most of the population in the calcium ground state, which is the lower level of the H and K lines, turns out to be much larger than the population in the lower level of H alpha, because of this big jump that Lyman alpha represents from the ground level of hydrogen. So even though you have much more hydrogen, the Boltzmann factor of the Lyman alpha line determines that the population numbers in the lower level of H alpha is much lower than the population numbers of calcium in the ground level of calcium, even though there's this almost 4 times a millionth abundance difference. Yeah. How are we doing with time? 10 minutes? Okay. Yeah. So some of the chromospheric lines that we won't talk much about, I've mentioned the calcium H and K lines. It's very difficult to observe them because you have low signal to noise. Although I've seen already some nice spectra, and so you can with this, but it's still tricky. For instance, one of the calibration steps that you do is to flat field, you need a lamp. And Roberto just told me last week that it's very difficult to do because a lamp is just what is it, 3000 Kelvin or so light source. And it doesn't have much intensity in these very short wavelengths. So just your signal to noise in your flat field is very small. This is just one of the practical problems that you don't necessarily think about when you want to observe the spectral line. It also, and we'll talk about this tomorrow, to properly model the line, we will need to take into account partial frequency redistribution, which is a mechanism that when you form a line and the scattering occurs high in the atmosphere, the time scale of excitation, de-excitation is so short that the line is not necessarily perturbed by any other particles. And in that case, scattering is coherent. And you have to account for the, in the emission profile of the line, you have to account for that coherence. And a fraction of those scatterings occur coherently. The other fraction does suffer perturbations by other atoms. And that fraction is completely redistributed. But, and that's why we use the name partial frequency redistribution. There's the magnesium B lines. On the first day, I pointed them out to you in the spectrum. I also showed them in the term diagram of magnesium 1. Magnesium B lines are fairly broad lines. They are good for magnetic field and velocity determination. The thermal sensitivity is a bit complicated. I will come back to that probably on Wednesday, because the magnesium B lines are neutral magnesium lines. And like in the case of calcium, even not as much as it in the case of calcium, most magnesium is in the form of ionized magnesium. But that means that you have to very carefully evaluate the ionization from magnesium, neutral magnesium, to ionized magnesium, because in the minority species, which is neutral magnesium, the populations are very sensitive to that equilibrium. For magnesium 2, that doesn't make much of a difference, but for neutral magnesium, you have to do that very carefully. And practically, this means that you have to have a very good measure of the EUV radiation field to properly estimate the ionization in magnesium, from magnesium, neutral magnesium to ionized magnesium. Again, is a typical complicated non-LTE problem that you have to be aware of and that you have to deal with if you use these lines as thermal diagnostics. Then there's the sodium D lines. You remember the lines typically in the yellow, the street lights that you see around are all sodium vapor excited by electrical current. And again, these are not sensitive. These are very scattering lines. They are not sensitive to the thermal structure, but they do have a good sensitivity because, again, they have fairly steep wings to velocities in the intermediate heights between the photosphere and the really hotter chromosphere. Then there's the very particular case of the helium 10A30 line. This is also difficult to model, and its interpretation needs typically the consideration of scattering polarization and atomic polarization, because of not so much because of its position in the term diagram, but because of its the energy differences between the different levels compared to the Zeeman splitting. There is, however, a very particular way that this line is populated, because, and we'll talk about in more detail, but helium has 2 electrons, and they can combine in spin. They can be anti-parallel or they can be parallel. And so this means that you have triplet lines and singlet lines. And the 10A30 is part of the triplet system. There is no allowed transition from the ground state of helium-1 to the levels that that connect the helium 10A30 line with the 10A30 line. And so the only way to populate those levels is ionization and recombination. And we'll see that in more detail. But this makes the sensitivity of the line very particular, and also makes that it is more sensitive to a relatively thin layer in the chromosphere, because of this mechanism, the way it's populated. So I think this is a good place to have a 10-minute break. Okay. Shall we start again? So in this second session, we will go in more detail about the equations and the transfer equation and how we solve it. To show you how the properties of the lines that we talked about in the previous hour relate to the equations that we want to solve. So let's talk a little bit about what we mean by thermodynamic equilibrium. Obviously, the solar atmosphere, this is a variation of the temperature in one of the VAL models as a function of, in this case, column mass. So this is the deep part of the atmosphere. This is the temperature minimum. This is the chromosphere transition region here. And these are, the diamonds are all the locations at which the model is specified. So clearly, the temperature in any of these height locations is different than from the other. So the atmosphere is not, the solar atmosphere is clearly not in global thermodynamic equilibrium, right? It doesn't have the same temperature everywhere. So what do we mean by local thermodynamic equilibrium? First, let's show that if we have local thermodynamic equilibrium, we have conditions that are determined by the temperature only. And this means that, I mean, people, as an example, draw like an oven with a little pinhole. And you can already imagine, and we'll formalize that in the next slide better, but you can already imagine that the pinhole is so small that it doesn't affect the thermal situation in the oven. The transfer of radiation or of energy through the pinhole is so small that the material inside the oven has time to equilibrate and to form population numbers, conditions, and radiation level at different wavelengths that are all compatible with one single temperature, right? So it's both a condition that is related to kind of time scales, where the time scales of equilibration is short compared to the time scale of energy leaking out through this pinhole. And it is a condition where there are enough processes that all the processes will be in how do you say that? I can't remember the term now. Anyway, that all the conditions in that air volume are only determined by the temperature. And in that case, we have the radiation field given by the Planck function. This is the formula for the Planck function as a function of temperature and wavelength, and the Planck function for different temperatures as a function of wavelength. This is the velocity distribution for the particles. Again, it only depends on the temperature and the properties of the atoms, of course. This is the velocity distribution for hydrogen atoms at different temperatures. And this is the velocity distribution, the Maxwellian velocity distribution for calcium for the same temperatures. And you see immediately there is a significant difference between the velocities in the calcium atom, the typical velocities that calcium atoms have compared to hydrogen, because hydrogen is so much lighter than calcium. Oh, this is not calcium. It's probably calcium. I wouldn't. Carbon is not that heavy, right? And then the relative population numbers. So if I have an atom in a certain ionization stage, then the ratio of the number of atoms in level J over that in level I is given by the Boltzmann fraction, where G is the statistical weight. This is the energy difference between the two levels, and K is the Boltzmann constant, T is the temperature. And similarly, we have a distribution for the ratio between two different ionization states, and it's given by the Saha distribution. And of course, in general, you will have both to account for the Saha and the Boltzmann distribution. And so you have Saha-Boltzmann statistics, as you say. So conditions that are necessary for local thermodynamic equilibrium. So I showed you the plot of the temperature as a function of column mass or height in the solar atmosphere. And so in each of those layers, you can imagine that local thermodynamic equilibrium is a good approximation. And the reason for that is that, or that is the case if the gradients in physical quantities are small compared to the distances over which the properties of the atmosphere change, right? So typical changes should be small, that in the sense that, no, I misspoke, sorry. So typical changes should be that the mean free path of whatever process of radiation or particles is small compared to the gradients, the size over which the properties of the atmosphere change considerably, right? And in addition, the time scale over which the particles and the radiation field come into detailed balance, that was the term I was looking for, with each other, and I have the same temperature, must be much shorter than the time scale over which energy streams in and out of that region. That makes sense, right? So in the solar atmosphere, typically the energy content in terms of the radiation field and the temperature distribution or the velocity distribution of the atoms is much larger than a typical dynamic time scale times the energy that streams in and out of it. It's like the atmosphere has a pinhole at the bottom and the top for each layer, right? This energy transfer is very insignificant compared to the energy content over dynamic timescales. And also, since radiation field is important, the opacity should be large enough that radiation cannot carry sufficient energy from one temperature to the other over timescale that are shorter than this balanced timescale. And this becomes more important in higher layers because there the radiation field can really affect the different population numbers of the atom in different ways, and therefore no longer be defined by thermodynamic equilibrium. Any questions, or it's clear? So let's go over, I mean, these are very similar to the slides that I showed, but I just want to have a natural flow of the slides from going from the processes that we consider to the equation of radiative transfer. So we have the specific energy, I, which is the radiative energy that flows through a location r per second per wavelength interval per solid angle in the direction L through the surface area dA. And this intensity is conserved. If you would put a similar little area here, then the intensity in both places would be, if you look in the same wavelength band over the same period in the same direction, this intensity is conserved if there's no emission or absorption in between the two. Then we have absorption processes, which I told you were proportional to the absorption coefficient and the intensity and the path length. We have emission processes which contribute to the intensity in a given direction with the emission coefficient J, and this emission contribution is proportional to the emission coefficient times the path length. And when we combine the two, we can write the positive and the negative contributions, bring ds to the other side, and define the source function as the ratio of the emissivity J over alpha, and then write the source function in this way, where we have also defined the optical depth or the optical path length as the emission or the absorption coefficient times the path length, and the optical thickness over a region D as the integral of this absorption coefficient over the path length. All straightforward definitions and derivations. So again, we have the source function, which is the emission per optical depth rather than the emission per geometrical path length. So it's defined as the ratio of the emission coefficient J over the absorption coefficient alpha. If we have multiple processes active at the same time, for instance, a line and a continuum process, or multiple continuum processes, multiple lines, we first have to sum all the emissions, and sum all the absorptions, and then take the ratio of those totals to form the total source function. So the total source function is then a weighted average of the line contribution and the continuum contributions. It's something that you have to be careful with, that you cannot sum source functions. Then we can write down the equation of transfer along a ray. And as we have stated before, the integral form of that is called the formal solution. The formal solution, because S, I told you before, in general is not only determined, is not a given, so this is not a closed equation, because S in fact in general will depend on the intensity itself, not only in the line but also in intensity at many different wavelengths in other spectral lines in the continuum, etc. Then let's introduce the concept of scattering and see how scattering affects the radiative transfer equation and therefore the properties of the line that we study in regions where scattering is important. Scattering is the process of a photon being absorbed by a particle or absorbed and immediately emitted. So scattering can also occur from an electron. An electron, Thomson scattering, can scatter an atom, scatter in a photon. And you have Rayleigh scattering, which is slightly different than the absorption and emission, which is the scattering that we will talk about in this context. In the context of non-LTE radiative transfer, we will talk about an atom absorbing a photon and in the same spectral line emitting a photon. Not necessarily in the same direction or at the exact same frequency, because that atom during the time that it is excited may be perturbed by other atoms in the neighborhood, and in that case you'll have complete redistribution, which we will talk more about tomorrow. But the essence of this is that there's no exchange with the local thermal pool. So there's excitation in the atom, then de-excitation via an emission in the same wavelength. But there's no contribution to the local pool, or that photon does not sense the local pool of the temperature of the local pool, because that excitation and de-excitation are independent of the temperature. So how do we formally include scattering like that in the transfer equation? We know that absorption is proportional to an absorption coefficient, and notice that I call it sigma in rather than alpha here to indicate that it's part of a slightly different process. In practice, of course, it is a sum of different processes, but to show the effect on the transfer equation of pure scattering, I call it sigma here. But since we said that scattering is really the case where you have absorption and subsequent emission of a photon in the same wavelength band, we can describe the emission as the same sigma times the mean radiation field, where the mean radiation field is the angle integrated radiation field. So since the scattering, we've assumed in this case that the scattering is isotropic. So the scattering source function is really integration of all the radiation from all angles that the atom sees. And so it is the mean angle average mean intensity. And so now when we write the source function of this pure scattering process, we see that the sigma drops out and that the source function is equal to the angle average mean intensity. This is very different than the Planck function, because now this angle average mean intensity, depending of course on the opacity, can come from a very different location, from area with a very different temperature, and therefore typically does not have the value of the Planck function. Of course, if the opacity is very large, then the radiation field cannot travel very far, and therefore then the radiation field will be equal to the Planck function. And so that's why I put that additional condition in the list of conditions for LTE, that really the radiation field should be come from an area that is close enough that it has the same temperature. In that case, the radiation field will be the Planck function. And so J will be B in that case. But in general, when scattering becomes important, J will have a value that is different from the Planck function. And therefore, the source function will no longer be the Planck function. So in the case of pure scattering, the source function is solely determined by the radiation field and therefore completely decoupled from the local conditions in the atmosphere. Unless again, the opacity is very high, and the radiation field is determined locally at the same temperature as the location that you're considering. And so therefore, this scattering process results in possible departures from local thermodynamic equilibrium. And scattering also tends to increase the effective path, mean free path of photons. If you have scattering, radiation field that comes from one area may propagate through the atmosphere unchanged by the local conditions to a very different part of the atmosphere. Right? So it becomes more non-local, if you will. So let's now write down the equations of radiative transfer when we have both scattering and absorption emission processes. So we have the emission profile, which has a thermal part that's described by alpha, and a scattering part that is described by sigma and the radiation field J. The absorption coefficient chi is the sum of the absorption and scattering coefficients. Right? So we write down the source function, and remember we have to sum first the emission parts, then the absorption parts, and then divide by the two. And so now using the equality epsilon is the ratio of alpha plus sigma, we can rewrite the equation in this form: 1 minus epsilon j plus epsilon b. And you can imagine when this epsilon is like a small value, then the spectral line that this source function describes is not very much coupled to local conditions. It gets very small contributions. Now this happens when epsilon is small, when sigma is much larger than alpha, right? So when the chance of a scattering is much larger than the absorption of a photon, and then a thermal exchange. And what the thermal exchange mean we'll define a little bit later. But just imagine that there's an absorption and then there is some thermal exchange with the local conditions. It's a very different case than when you have a scattering event where you have a absorption and emission without any thermal exchange. So this source function, depending on the value of epsilon, behaves more like the radiation field or more like the local temperature B, depending on epsilon. When epsilon is small, it behaves more like the radiation field, and when epsilon is large, it behaves more like an LTE line, where the source function is given by the Planck function. Yeah. Then we can, and this will be useful for later on, we can write the angle average mean intensity, J, as a operator lambda operating on the source function. And you can see that this way, in that the J, the angle average mean intensity, is the angle integrated intensity. And that is substituting I with the formal solution. Right? It's just the integral of S over tau. We can write this as an operator lambda operating on the source function. Yeah, this is just a formal way of writing things, but it indicates that the angle average mean intensity depends on the source function in a way that through the operator lambda that operates over different elements of your path that you're looking at. Okay, so typically we don't have just two levels to account for. In the case of calcium, if we want to do non-LTE radiative transfer, we fortunately only have to account for these 5 bound levels and calcium 3, so ionizations from any of these levels. And the reason I show you this is just to make you aware that if we want to calculate the properties of this line, one of the H and K lines here, we have to also calculate the radiative transfer in any of these 3 lines and in the ionization transitions. So we have to solve both for the collisional excitations and de-excitations between these levels and all the radiative transitions between them. And we'll formalize that a little bit later, just to make you aware that this is how the different levels and lines are interconnected, and radiative transfer has to be solved globally, not only globally over the whole atmosphere, but also globally for all important levels or relevant levels in the atom. So what are let us now formalize the different ways that you can have a transition between 2 electronic levels in an atom. So we have level E1 and E2, which might be, for instance, the low level of the calcium H and K lines, in this case, the ground level of ionized calcium, and the first excited level. Well, not the first, but the one of the P levels in the diagram, right? In this, so it might be one of these levels, right? And we have a photon of exactly the right wavelength, and it can excite this electronic level from E1 to E2 with the absorption of a photon, right? And of course, the wavelength and the energy difference between these levels is related this way. And then we have 2 processes which are not immediately obvious. We can have a spontaneous emission, where the atom changes from level E2 to E1 by emission of a photon, again of the same wavelength. Or we can have stimulated emission, and the fact that stimulated emission existed only came once people started to compare the excitation and de-excitation, comparing with a Planck function. And there was, in the Planck function, there was a term missing that had to be there through this process. Otherwise, the Planck function would not match the excitation and de-excitation rates. So stimulated emission is basically an excited photon. You have a photon coming by, and then there will be emission of a photon of exactly the same wavelength as the photon that came by, and there will be a de-excitation. Then we can have the same transitions, but as the result of energy transfer by an electron that collides with the atom. So you have the same 2 energy levels, and you have an electron coming by of a certain energy that is larger than the energy difference between the 2 levels. It will excite the atom from E1 to E2, and then afterwards the electron has a kinetic energy that is EB minus EA. It will have a kinetic energy of EA, where the EB that is imparted on the energy is the energy level difference between the 2 levels. And similarly, you can have a collision with an electron that takes away the excitation energy. So it's a reverse process of this. So when you have large electron densities, as you have in the photosphere, this process of collisional excitation and de-excitation dominates by far over the previous slide, where you have radiative excitation and de-excitation. In the same way, we can have ionization and recombination by radiation field. So we have an atom in energy level E1. We have a we have a photon of high enough energy. It can ionize the atom, which means that the one of the electrons becomes unbound. The ionized state has fewer electrons and therefore has a negative charge. It becomes an ion, and the energy difference, or the energy excess energy of this photon compared to the energy difference between the this level E1 and the continuum level is taken away by the unbound electron. And you can have the reverse process where you have a similar process that is analogous to stimulated emission, where you have stimulated radiative recombination in the same way. And again, we can do the same kind of transitions by electron, and you can go through the energy terms. It's all very straightforward, but you can have collisional ionization, where the electron basically strips an additional electron from the atom, and you can have collisional recombination, where the most important part of that is that you need 2 electrons. So collisional recombination is a 3-body process, because you need an additional electron to take away the excess energy. So this process of collisional recombination, the fact that this is a 3-body becomes important very high in the atmosphere, where the time scales over which ionization and collisional recombination occur can become very different, because the lower the density, the less frequent this process becomes, and it can become so unfrequent that the time scale over which it occurs becomes longer than the dynamic scales in the atmosphere. And so then you will have non-equilibrium ionization in hydrogen. This is a very noticeable and an important effect. So now let's write the formal equations for emission absorption for these processes that we lined out in the previous slides. The emission coefficient for spontaneous emission is the number of atoms in the upper level of the transition that you're considering, times this is a constant, Einstein A coefficient, which is kind of indicative of the strength of the transition, the probability that it occurs. These are really quantum mechanical terms that you can derive the value of these from the structure of the atom and quantum mechanical considerations. And then there's the absorption profile phi. Yes. So we showed this before. Typically in the solar atmosphere, this line profile coefficient is the Voigt function with damping wings A that depend on the damping width, which can have contributions from the natural width of the line, and collisional broadening by mostly hydrogen through the van der Waals process, where hydrogen atoms collide with the atom in its excited state and then perturb and broaden the energy level and therefore the line. So we can write down the equation for stimulated emission. Again, this is proportional to the upper level population number. But in this case, the proportionality coefficient is the Einstein B coefficient, where AJI and BJI are related this way. And this comes really from quantum mechanical considerations. And then we have the absorption coefficient, which is, of course, proportional to the lower level population number, Ni. And Bij and Bgi are related through the statistical weights of the 2 levels. Again, you don't have to remember this. I'm just writing you down these equations so that we can derive the properties of the transfer equation with these kind of transitions and show you the proportionalities of the different processes. So now if we combine all these coefficients in the transfer equation, so now we write down the transfer equation only as a function of one spectral line. So I don't consider contributions from the continuum. I don't consider contributions from other spectral lines. I purely write down the source function in the case I have two levels that are connected by one spectral line. Yeah? And in this case, only the radiative contributions, not even the collisional contributions. So we can combine this by just substituting the values for these properties, and then we can derive the source function. And it looks like this, that it is proportional to the upper level times the Einstein A coefficient divided by the lower level times the Einstein Bij coefficient minus the stimulated emission term. And typically this is much smaller. So typically the source function will be proportional to the ratio of the upper over the lower level population numbers. This is important to remember for what we are going to talk about, that this proportionality of the upper level population numbers. And using the relations between the different Einstein coefficients, we can rewrite it in this form. You see already that this looks very much, this is reminiscent of the form of the Planck function, right? And so you can imagine that this stimulated emission term is there because of the shape of the Planck function. When you look closely at what the shape of the Planck function is, this term has to be there. Then we have the radiative rates. So the radiative rates is the total rate of transitions because of the radiation field. So the total rate of excitation and de-excitation given the radiation field. So formally we can write the radiation as the integral over all wavelengths times the absorption profile of all the radiative transitions from level I to level J. And this is can be written as Bij times this J bar, which is very similar to the angle average mean radiation field, but it does have this additional line profile there. So it's really an integration over the line profile. If you will, it's the angle average mean intensity integrated over the line profile and all angles. And similarly for you can write also the stimulated emission. No, this is the absorption, right? So this is the so I'm sorry, this should be Ji, of course, right? This is the stimulated emission plus, or the spontaneous emission plus the stimulated emission, which you can see is very similar to absorption, except you have Bji instead of Bij. Yeah. So so again, this should be Ji, not Ij. So now let us consider the formation of a specific spectral line. As I told you before, we now have to consider all the possible transitions between all these energy levels. And we assume that we have statistical equilibrium, meaning that we have a situation that doesn't change with time. So we have excitation and de-excitation in the atom that we are considering that is in equilibrium with the radiation field and with the local conditions. Doesn't change. So the population numbers do not change with time. So in this case, if we consider a certain level, we have to consider that, so a level I, for instance, we have to consider that all excitations from that level to different levels, to different level J, equal all the transitions towards that level, right? We have statistical equilibrium. So these total rates in and out of level I should be the same. Yeah. So, but you can already see that in general, this set of equations, so this is a set of equations for the population numbers, and J and I. And we have the same set of equations for each level I. So you can already see that this set of equations for all levels in generally form a nonlinear and non-local set. Why do I say that? It's nonlinear because these R's contain the radiation field. The radiation field through the equation of radiative transfer depends on the population numbers, right? So we have a nonlinear equation because there's population numbers involved in this R. But we also have a non-local because the radiation field that is represented by these R's, by these radiative rates, contains radiation that can come from very different places in the atmosphere. So this, to find a solution for the Ni and Nj, which we need to calculate the line profile through the radiative transfer equation, constitutes a nonlinear, non-local set of equations for the population numbers, Ni. Now, if we consider an atom that just has two levels, level 1 and level 2, and we don't consider any other levels, it's called a two-level atom approximation. We can write down very easily the total statistical equilibrium equation, because we have excitations or de-excitations from 2 to 1 through collisions and spontaneous emission and stimulated emission. And we have absorption in this term and collisional excitation. Yeah, so the statistical equilibrium just becomes one equation where we can use that the collisional excitation and de-excitation are related to each other in this way. Then, if we, in addition, write down the source function and use in a smart way the statistical equilibrium equation, we can actually write down the source function in terms of this J bar, the integrated angle average mean intensity over the line profile. And this is an exercise that, if you have some time, you should try. It is not as trivial as it looks. It requires you to really carefully look at the equations. But using the equation, the expression for the source function of the line and the statistical equilibrium equation, you can derive that the source function can be rewritten as 1 minus epsilon J bar plus epsilon B, where this is epsilon. So epsilon is called the collisional destruction ratio, because it is the ratio of the rate of collisional de-excitation divided by the total rate of by the total rate of de-excitation. So it is a measure of the fraction of atoms that get collisional de-excited or de-excited through spontaneous emission or stimulated emission. So you can imagine that it's kind of a measure for the importance of scattering, right? If you have collisional rates that are much larger than the Einstein A coefficient, you'll have this epsilon very close to 1. So we have the case where in a single wavelength scattering, the equations that I put before, you have a very small scattering contribution. So you almost have a LTE line when epsilon is large or close to 1. When this Einstein A coefficient becomes much larger than the collisional de-excitation rate, scattering becomes much more important, because whatever is when you have an absorption, you have a much larger chance of a spontaneous emission than a collisional de-excitation. And this is exactly what scattering is, because in this case we have a two-level atom. There's only two ways to change from level 2 to level 1. And so we can write almost exactly the same form as the single wavelength scattering that I introduced a few slides ago, with the difference that in this case we don't have just J at the given wavelength, but we have the J bar, which is the angle average mean intensity over the line profile. Yeah, and this is then the shape of the Planck function. So using all these things, you can rewrite the source function in this way. Is clear that the single wavelength scattering problem is almost has the same expression as this two-level atom source function, but they contain very different considerations, but the mathematical shape is exactly the same. So recapitulating, we can write the source function as the operator lambda working on the source function. So this is, you can imagine, this is very similar to the formal solution, right? Where we don't have a closed equation because we have the source function on both sides. And this is an operator. We cannot just write this out and bring source function to the other side. So now, how do we solve this equation? Obviously, it's a non-local, non-linear equation because what the non-linearities are in this lambda operator is not immediately clear. But we've shown that when you look at the population numbers and the source function depends on the population numbers, you have a non-linear set of equations for the population numbers. So this is a non-local, non-linear problem. How are we going to solve this? So let's try the simplest solution. Let's try the first guess and say the source function is like the Planck function. This is a very straightforward solution. So we can then define the next iterations of the source function as the source function, this estimate substituted in here. We can evaluate the whole right side, and we have a new estimate of the source function. Formally, we can write this in this way, that the source function depends on the previous iteration of the source function, and we get a new estimate of the source function. How well does that work? Well, if epsilon is small, in this case, epsilon is a half. These are the different iterations. These are called lambda iterations because we just apply the lambda operator to the previous estimate. So these are called lambda iterations. You can see that it might work. We do 10 iterations and we get close to the actual solution. If we have a constant source function over this domain and we have a constant value of epsilon, we can actually solve the equation analytically. And this is what is here, the dashed line. So this is the source function that we start with, our initial estimate, S0, which is just the Planck function set to 1 because we doing unitless calculation here. Then in 10 iterations, we would be okay. And this is a very simple problem. So 10 iterations in a one-dimensional atmosphere would not be a big deal. Would be feasible. Now, epsilon is 0.1. And you see, well, now we're going to need 100 iterations, which again, in a one-dimensional two-level atom is not a big deal. And computers are fast. Computation time is easy. So it's still maybe doable. But this is only 0.1. And I've showed you before that epsilon typically goes down to 10⁻⁴ in the chromosphere because Einstein A coefficient is so much larger than the collisional de-excitation rate. Because the collisional de-excitation rate depends on the electron density. I haven't shown that here, but that's the case. The rate of de-excitations and excitations by collisions is proportional to the electron rate. So you go high up, densities decrease exponentially with height in the solar atmosphere. Collisions get smaller, and collisional rates get smaller and smaller, while the Einstein A coefficient is only dependent on the atom properties, so it stays constant. And so this epsilon in reality becomes very small. And then when epsilon becomes 10⁻⁻3, lambda iteration is no longer a viable solution because I have to iterate forever, hundreds of times, thousands of times. If epsilon is 10⁻⁴, this is what 100 iterations get me. It's maybe halfway. But in reality, when you look at it, you need about 3,000 iterations in this simple case to get to the solution, which no longer becomes very practical. even in cheap cases like this. So we will have to find an alternative solution to the transfer equation. This lambda iteration process is too slow and too undetermined. You don't have a really good feeling of when you reach convergence, actually. So as I told you, we need about 3,000 iterations in this case, if even when epsilon is 10⁻3. Now there is a much better solution to this, and it's called accelerated lambda iteration, where you realize what the problem is and you physically introduce an analytical improvement to this equation that makes the convergence process of your iterations much better and faster. And there's a good physical explanation for why this works. So again, we have the transfer equation written as the lambda operator here, and say that for a one-dimensional array, this is really an equation that this operator depends on different positions along the line of sight on K. Different locations in the atmosphere. It's, this is kind of an integration over depth, if you will. So now we can introduce so imagine if lambda were just a local operator, so it would be active only in one point, right? In point K. Then you could actually bring the source function here to there, and you would be able to write an analytical solution for this equation, right? Now, the trick that we are going to do is that we split this lambda operator into a local part that is diagonal and that we can analytically bring to the other side, and a non-local part. And so we apply a technique that is called operator splitting. And when we do that, so we write this local operator here, lambda star, plus some correction of J, where this J is the actual lambda operator. Oops. The actual lambda operator at depth K minus the local contribution. So we separate that out. And when we substitute that, we can describe a new iterative scheme where we likewise start again from the first iteration. We start from the Planck function. But now we write this additional equation where we separate out the local part. And because the local part we can bring S to the other side, we can write this in this manner. And now the diagonal part can be directly inverted and brought to the other side. And we only have to iterate numerically the off-diagonal parts, which are much weaker. So the way to think about that physically is that when scattering is important, the scattering occurs locally. So you have, if you analytically eliminate all the excitations and de-excitations that occur locally from the local radiation field, then the strongest part in the scattering is treated analytically and brought to the other side. And you only have to deal with the non-local aspect of the off-diagonal terms, which is a much weaker effect. And when you do that, you can go after the lectures, or when you have time, you can go through these equations. I can imagine that you cannot exactly follow how the equation is, but if you apply that simple analytical change in the equations, you only, for 10 to the minus 4 epsilon 10 to the minus 4, you only require 142 iterations. So this is very different than 30,000 iterations that I would require if I would just lambda iterate and I would deal with the non-locality or the non-linearity of the local part, not analytically but numerically. Yeah? So this is important to remember, that a similar technique will be applied once we deal with more complicated situations than just the two-level atom. That analytically you can take out the local operator mathematically and bring it to the other side, and then deal only numerically with the weaker off-diagonal elements of the lambda operator. So
on real quick, is there a loss of numerical precision in the second approach, or do they converge to the same solution?
No, because they you can go back to the equation. Once you reach the solution, the same equation applies. So there's no loss of it. So you have a faster path, but the equations describe exactly the same solution. That's the whole idea of operator splitting, where you have an iterative process that has a different path through solution space, but it ends up at exactly the same. When the difference between the real solution and your solution is 0, it's exactly the same solution, independent of how you got there. So this is now a spectrum that is calculated from a standard atmosphere Val model compared to the Atlas spectrum in the calcium H and K. And you see, in general, there's very good agreement between the two. There are some differences, and we have very good agreement. So how do we reach that numerical solution when we have a radiative transfer problem that is more complicated than just the 2-level, where we do have to account for the 5 different band levels, the 5 different spectral lines, and the ionization and recombination between the calcium 2 and the calcium 3 levels. We've seen the equations already, but let's go through them again. So we have a model atmosphere where we specify the velocity, the temperature, the density, the electron density mostly, at different heights in the atmosphere. We have a calcium model atom where we know all the transition probabilities. We know the collisional transition probabilities as a function of electron density, of temperature. We know all the radiative rates. And so we can now combine that through 2 equations, the equations of statistical equilibrium and the equation of radiative transfer at all the relevant wavelengths. And we can write down the radiative rates as a function of the different atomic and atmospheric quantities. We can write down the equation of statistical equilibrium for all the levels. And then we can solve the radiative transfer. Now, imagine 2 locations in the atmosphere. And deep in the atmosphere, in the photosphere, I told you the collisional rates dominate. The radiation field is, the material is very opaque. So the radiation field is also very locally determined. It's very close to the Planck function, actually. And so excitation and de-excitation here, the ratio of these 2 levels that connect the 2, or that are connected through the spectral line we're considering, is very close to Saar-Boltzmann statistics, because both the radiation field is locally determined, and collisions dominate. Now consider a location higher in the atmosphere. You know that the electron density falls off exponentially, not quite, but because of other reasons. But densities fall off exponentially, collisional rates sharply decrease. We still have a radiation field that comes from below that is very much close to the Planck function. But now, since you are close to the upper boundary of the atmosphere, the radiation field is able to escape, and nothing is coming back from that, right? And so now this radiation field is no longer able to maintain, because the population numbers here depend mostly on the radiation field rather than electronic excitation and de-excitation. The population numbers of this upper level fall below the Saar-Boltzmann levels, right? And so if you remember, the source function was dependent on the ratio of the upper level over the lower level population numbers. So now when this population numbers of this upper level drop below the Saar-Boltzmann values, the source function will drop below the Planck function, because we have radiative losses to the outside world from which nothing returns. Yeah. So the source function in these non-LTE conditions typically will fall below the Planck function because of radiative losses. Yeah, is that clear? So when we go through these solving these equations numerically, and I haven't really told you how to go from a numerical solution of the two-level atom where you can write it as a single scattering problem to a solution of a multi-level atom with all the radiative transfer. But it goes in a very similar way with an operator splitting, where you write down the radiative transfer as an operator operating on the different population numbers, and you can do an operator splitting and in the same very similar way solve the radiative transfer numerically with this accelerated lambda technique. So once we do that, we can now start to understand the very particular shape of the calcium H and K lines. Remember that when we have a source function that decreases with height, we have an absorption line. When we have a source function that increases with height, we get an emission line, right? But the H and K lines have these emission reversals in their core. And so they seem to be something in between. How can we explain that? Well, this is a bit of a complicated plot, but this is in red here. We have the Planck function as a function of height. In this case, I've plotted it as column mass, like in one of the previous. So this is just a measure of height deep in the atmosphere, temperature minimum, chromosphere, so the temperature rise, and the transition region. So you can see that the temperature initially decreases, then is temperature minimum, temperature increases, right? This is now in black here. We have the source function in the line wing, and these arrows are where optical depth is unity. So if we look at the simple Eddington-Barbier relation that I told you when we talked about the Milner-Eddington, where the emergent intensity is more or less the source function as optical depth unity. So this is the middle angle, the middle arrow here. So if we follow the intensity, we see that initially the intensity at this wavelength comes from a source function that decreases. So if we go in the line, then more and more the source function will be sampled at a higher and higher depth, right? And the intensity will decrease because the source function decreases with height. Then we reach the temperature minimum, and we get this minimum here in the line profile. And then we start to see the temperature rise, but the source function here in black does not follow the Planck function like it would for an LTE line. But this is a non-LTE line, and higher up in the atmosphere, we saw that the source function, because the population numbers cannot no longer be maintained because the radiation field falls below the Planck function. The source function falls below the Planck function, and so the source function here gets decoupled because of the scattering. Oops, gets decoupled, and so while we reach a maximum somewhere here, the intensity for the wavelengths closer to the line core decreases again, because again we see a source function that decreases with height because of the effect of photon losses in the line, right? So this is really the non-LTE effects, but specifically in the line that we are considering, where the population number of the upper level and therefore the source function can no longer follow the Planck function because we have radiative losses to the outside world. So this is the quintessential non-LTE radiative transfer effect, if you will. So I think yeah, we can skip that. Oh yeah, there's one thing that I wanted to say. So I told you that the line or the observation that told us there is a chromosphere is the H alpha line during a solar eclipse, right? It clearly shows us the chromosphere. but there is an kind of an ironic twist in that, if you calculate the spectral line profile with an atmosphere of H alpha, with an atmosphere that is a radiative equilibrium atmosphere that does not have a chromosphere, and you calculate the source function, which turns out for the line H alpha line to be a scattering source function, no matter if you have a chromospheric line or not, a chromospheric temperature rise or not. So this is the case where you have a chromospheric temperature rise, and well, in this case, you have the temperature as indicated here by the values of the Planck function just goes flat towards the atmosphere, right? And you look at the shape of the source function here in black, which is almost the same as the J here, or at least follows a J because it's a scattering source function, right? It's almost the same shape here. The emergent line profile, I missed it. So you can plot the emergent line profile, and it's almost exactly the same for an atmosphere that has a chromospheric temperature rise or an atmosphere that has a thermally flat temperature distribution. So ironically, the twist is that the H alpha line is exactly the same. So the line that told us that the chromosphere is there is actually not sensitive to the temperature, in at least not in this sense. It has very little temperature sensitivity in its source function. So that was just like a note that you really have to understand how your line forms if you want to infer properties of the atmosphere from it, right? So that's, I think, let's see. So yeah, so when it's, in summary, when is non-LTE transfer important? It's important when, so when density is high and collisions are frequent enough, population numbers are determined by the local conditions, right? They're given by the Saha-Boltzmann at the kinetic temperature of the gas. The radiation field is then given by the Planck function. When opacities are high enough, it's locally controlled. When densities drop at height, collisions become less frequent and radiative transitions become relatively more important. The population are now determined by the non-local conditions, namely by the radiation field that comes from different places in the atmosphere. And we need to find, for radiative transfer, we need to find a global solution, not only in space, but also in wavelength, where we have to consider different radiative transitions that combine and connect all the levels, the energy levels in an atom by different radiative transitions. So I think that is the, yes, that is the last slide. Any questions? Yes.
So here in the discussion, whenever we are talking about space, it's mainly the variation with height. It's not
so in this case, we've talked mostly about, since all the examples I've given were just one-dimensional plane parallel atmospheres. But in general, when you have a 3D situation where you have spatial inhomogeneities, the radiation field, of course, becomes a more complex quantity, where it not only depends on the structure below the point that you are considering, but also points on the side where you have horizontal radiative transfer contributing to the population numbers through the radiative transfer.
So in like proper whatever codes we use, that consideration is also taken. Maybe you will cover it next
So
time.
if you use a 3D, so if you were to use RH3D, the 3D version of RH, that all of that structure is, or the dependence is taken into account. You really calculate the radiation field coming from all directions, where they are properly integrated along those directions. If we make the assumption that we have a one-dimensional plane parallel atmosphere, you assume that the atmosphere is thick enough or thin enough compared to the horizontal extent of that horizontal radiative transfer can be neglected. That is the assumption you make when you go to one-dimensional plane parallel radiative transfer.
So in the theory lectures, maybe further tomorrow, are we going to cover this thing, or you plan
Well,
to just
maybe I will I can put in a slide, but you can show actually with an analytical approximation that when you have a exponentially stratified atmosphere, the radiation field in the vertical direction is much more important than horizontal radiative transfer. So horizontal transfer is a typically small correction to the transfer in the vertical direction because of the exponential stratification of the atmosphere. So typically, you only have to worry about structures that are larger than a few scale heights. So you can show that with a simple analytical analysis. You can show that for structures that are smaller than that, you have to worry about it. Yes.
So was H alpha and all the Balmer lines used at all in creating the VALC, the foul models and so?
I think so. I mean, as you know, and I haven't mentioned that, there is, of course, a sensitivity of the H alpha opacity and not the source function. So to the thermal width, right? And so you do have the shape of the line changes with, but it's a subtle effect, and the depth of the line does not depend on chromospheric temperature whatsoever. You always get the same line depth.
So the lines, maybe the calcium and the magnesium lines, were in a sense more critical in building.
Yeah, sure. So certainly the emission in the calcium H and K lines were a large factor in doing the inversion by hand that led to the VAL models. Yes. Okay.
So with the accelerated lambda iteration, I'm having trouble conceptualizing why the off-diagonal elements, so like the non-local effects, are intrinsically weak. Especially, I guess, thinking about.
Yeah, so numerically, you can imagine that when scattering is large, then in one local point, the amount of excitation and de-excitation is very similar but opposite in the statistical equilibrium equation. While because of optical depth effects, the effect of the radiation coming from other locations is attenuated because you have absorption in between. So those elements that contribute to the scattering in a local part are small, because you have to eat the e to the minus tau effect.
Just wonder, when you're calculating the collisional recombination or radiative recombination, is autoionization also important?
You can, but if you have the coefficients, you can specify them and they can be included.
Okay.
So it really depends on which physical processes you include in the code, right? You handle or not. And I think you can, if I remember, because I almost never deal with it, but I think I have the processes included. So you'd have to know the coefficients for auto.
Okay, thank you.
And otherwise, it would not be too hard to add them. Okay. Okay. Sorry, Carlos.
Good. So before starting, I just want to mention, so first, that we will do almost the same type of tutorial as last week. So if you can join to Zoom, and then you can share your screen when we have some results, it's better. And then I forgot to show you last week tutorial 6b. And the main difference is that when you compute response functions and you have a magnetic field, the code will always write a file that contains the 4 Stokes parameter. But if the magnetic field is 0, then automatically the code will run a response function file that only has a Stokes high. Okay, so then in that sense, there's another function inside. Sorry, there's another function inside the read-write.py script that is for reading the response functions when you have magnetic field 0. So we will probably check this example today or tomorrow because we will have time, but it's just that. So if you are computing response functions with an atmosphere with 0 magnetic field, then you need to use the function called, I think, read FRI. That will just read Stokes I. But probably we will check. And if not, just remind me and we will take a quick look. Then the second thing is that before starting with the presentation, I revised a bit the desired tutorials over the weekend. So if possible, download again all the folders because there are some minor changes in some things. And then you can create your own folder for following the class, but doing some changes. Do you have the link, or should I share it again through the chat in Zoom? It's fine. Okay. Okay. And while you are downloading the data, just to mention that we are going to cover an inversion code that can do inversions in non-LTE. My feeling when I try to understand LTE process is that it requires time, but as soon as we move to non-LTE, it requires much more time. So, example, Hans' slides this morning, every time here I put a new slide, I remember that it was taking a lot of time for me to get the concept. So even if it's very difficult, we are going to follow the SARE concept, and we are going to mainly focus on understanding how to run the code and understanding the input that we need. But I will try to make it as simple as possible in terms of what is the code doing inside. This will be probably Han will help us understanding that. And if not, I can help you later on. But the tutorial will be more like last week. So trying to do exercise, someone will change something, it will work or it will stop working, and we will try to understand that. And I will not try to show not many equations or other things, right? So just trying to get the feeling of how to run the code without entering too much on how it works inside. Okay. So then, as before, it's just a 2-slide presentation. So then this side, it's based on SARE that you probably know from last week. And the main condition of SARE is that it works in LTE and it's based on response functions. Okay, and what we know from all these 30 years, I think this year is the 30th anniversary of the SARE inversion code, is that it has been evolving, but the base of the code is very fast. And maybe is it okay? Because I hear some, yeah. Okay. How about now? Better? Okay, good. Yeah, thank you. So then the idea is that we now want to analyze chromospheric lines. And as Hami was explaining this morning, those lines, they don't follow the LTE approximation. So then we need to add somehow non-LTE effects in the computation. In general, there are several codes that can do that in the literature. But in their cases, although they are based on response functions, they are usually using either numerical response function or a hybrid approach. But in all the cases, it requires a lot of time for doing an inversion. So then we decided a few years ago to make a code that somehow it's complementary to those codes, where the main target is to make it faster. And then the idea was to keep using the analytical response functions from SER that we know they are fast and reliable, but that somehow add a correction that includes the information of the non-LTE process that is required for experimenting chromospheric lines as an ad hoc element. So then the idea is that, we are going to compute departure coefficients, that they are how much the population of a given atomic level deviates between LTE and non-LTE, and we will add that as an external correction in the simple, fast and reliable process that we are doing with SER. Okay, so then the process will be fast and reliable, and we will have an impact on the speed because we will need to compute these departure coefficients, but we will not need to do it in every cycle, in every iteration, like it is done in the other codes. It will be just done a few times only. Okay. So then, when starting, we thought that probably the best code to get the non-LTE population for departure coefficients is RH. I think tomorrow you will get an introduction. Basically, you can think of this side as a combination with a good dialogue between RH and SER. We have integrated them, we have improved some things in the way, but essentially is that. So we run RH to get the accurate atomic populations of all the levels involved in the transition of interest. Then with that, we compute the departure coefficients, and then we provide that information to SER, and we run the same analytical response function inversion, but adding the correction or the deviation from LTE that we get from this side. Okay. You can find the details in the publication. It's a long one with a lot of equations. So if you want to really get on insights on how the code works, I recommend you to read it. It's also in the Dropbox folder. So I think in publications, you have this paper as well, so you can read it there. And then, sorry. And then, as I said, it works as SER. So then let's try to recap. Let's try to recap. It's because this screen is showing different things, so sometimes I get confused. How SER works. So in the case of inversion, we had an input profile, that is our observation. We feed the code with this input profile. We have an initial atmosphere. Then we tell the code, I want to change this atmosphere or the atmospheric parameters of this atmosphere in several nodes positions. We run several cycles. Those changes, or how much the code is going to change the atmosphere, is estimated based on the response functions of the Stokes parameters to changes on the atmospheric parameter. And then when we finish the cycle, we get an output atmosphere, the profile that is synthesized from this output atmosphere and should be very close to the input one, and an estimation of the error. Okay. So essentially, we are going to do the same now. We will see that we add some minor things in the middle, but the process is exactly the same. The control file is almost the same. The input, the format for the input files, the output is still the same. So then I think it will be very easy for you to follow the process, but I will try to stop on the new additions a bit longer, just to allow you to see that it's getting a bit more complex, but in general, the global picture is the same. Okay, so if you got it last week, you will get it today, and if not, it will allow you to. So we will revise today how the code works. Okay. And this is essentially what I said. So we don't need to enter in this too much. So yeah, and also and also we are going to learn. So we learned in serial. We are going to learn today and tomorrow decide in serial, but we have created Python wraps that they would just take a cube of data, distribute it, and then run the code in parallel, and then we'll get back with the cube information. We will not cover it here, but it's in the online tutorials. And if not, just send me an email and I will give you some hints of how to run it. And then you will be able to run it in parallel, either in servers or either on clusters. I usually use it on servers, but it has been also tested on NSO new cluster, and it also works well there. So depending on your resources, you can choose any of the options. Then the aims are the same. So we would learn how to prepare the configuration files to run a synthesis. We will do the same process. I will create one atmosphere. You will create another atmosphere just to do some tests, just to play a bit. Then we will synthesize the profile. We will add noise, and then we will prepare everything. Also prepare the atmosphere, the initial atmosphere, and then we will embed the profile. Again, you will have one profile, I will have a different one, we will compare the results. And then finally, with the output atmosphere that you will get, we will compute the response function. Okay. And then I have a second option that if everything goes fast, then I have profiles from a 3D numerical simulation, and that's much more complex, and we will use for doing the synthesis, and then we will add noise, and then we will embed, and we will compare how the code behaves in this scenario. Okay. So as again, we have a lot of tutorials in the channel. So I recommend you to complement what we are learning these days here with this information. But you can just contact me if you have any questions. Sometimes it's easy than watching 3 hours of videos. And we have a GitHub from the first author, that is Basilio, but he usually goes slow, so soon you will have the code there. So just take note that it should be in GitHub, and soon it will be there, but now it's not there. So it's so the link that you have that points to the code in Dropbox, in my Dropbox, I will always keep the newest version there. So if you keep the link, you will always have access. And also in the YouTube tutorials, always the link that you have there is pointing to my Dropbox folder, where I always keep the most updated version. So you will be able to get access, but not through GitHub. It will be through my Dropbox folder. Okay. So that's all as an introduction. Do you have any question so far? No? Okay, then let's start. We go again, so we are in this side. So this is the folder that I'm sharing with you. So we go to this side, and then we enter tutorial 1. Open tutorial 1, then this is one. So how about this? Can you see it, or should I make it a bit bigger? Is it fine? Yeah, okay. So tutorial 1, just 1 second. So then I assume that all of you downloaded the code and compiled it in your computer. Any issues running it? No? Okay, so then we just go. So I think we can skip this because we are going to do it later anyhow. So then input files. We start with atmosphere. Now I can go a bit faster because it's essentially the same file. So in this folder, we are going to use again HSRA atmosphere. And remember that it was like this. So a header with 3 elements: macro turbulence, filling factor, straight light, and then 11 columns. Log tau, so optical depth at 500 nanometers, temperature, electron pressure, microturbulence, field strength, line of sight velocity, field inclination, field azimuth, geometrical height, gas pressure, and gas density. Okay, as before, the last 3 columns, they are just computed after the process is finished. Through hydrostatic equilibrium, you will get geometrical height, gas pressure, and gas density, but they are not atmospheric parameters that we can invert during the process. We always invert temperature. In principle, electron pressure can be inverted, but usually it's not something that we will do. Later on, I can explain you why. So essentially, it's the same 3 parameters that we use with CERN. So temperature, magnetic field vector, line of sight velocity, and then you can have microturbulence, macroturbulence, and the other parameters. But essentially, it's the same. Okay. So then this is a description, and I can run it until here. Check again. 3, 1, and this is the atmosphere. So the HSRA atmosphere. And then the only thing that is important now to keep in mind is that we are going to create it in the same way. But if you remember with photospheric lines, we said that basically our atmosphere can end around tau -4 because the sensitivity of the lines are generally around this region. But now we are working on LTE. So then the sensitivity of the lines can reach -6 or -7. So in general, now we are going to use a wider extension on optical depth because atmospheric, the chromospheric lines, they reach much higher in the atmosphere. Okay. Then let's start playing a bit. So I remove this comment, and then I put stop here. So you can also put a stop on 182, and then just create an atmosphere different than the one I have. Remember that now I put the labels, so you know temperature, microturbulence, magnetic field. So just create one that you think could be interesting to check in. Remember that I put everything flat, but you can add gradients along the line of sight for velocity, magnetic field. Okay. Water while you're doing this. Okay, so how are you doing? Finish already? Then let's discuss what type of atmospheres are you using. So who wants to tell us very briefly the atmospheric parameters they use? So let's start for rows or columns. So how about this column? Who would like to tell me? Brian, for example, which atmosphere are you using? Okay. How much? 80? 80 flat? 88 and flat. Okay. So you want a very inclined magnetic field. Okay. And how about velocities? Okay. So a gradient along the line of sight, or the same that I have? Okay. Okay. Good. Vincent, how about you?
At 3,500.
Okay.
Inclination 85. I increased there.
Okay. Okay.
And everything else. So I increased increased line of sight.
Okay. So how much line of sight velocity?
1.5.
Okay. Okay. Good. Good. Yeah. Okay. So how about the middle or the third row? So Dushan, how about you? Okay. Okay. So the gradient in magnetic field, the amplitude more or less is like between 200 and 400, or from 1000 to 200. Okay. Okay. So how about this right side? Saida, how about you? Yeah. Okay. 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 So decreasing and then increasing again? Okay. So this is the magnetic field. So some kind of like parabola like this. Okay. That's interesting. And also it's good to that she's doing something like this, because sometimes in general, we expect that the magnetic field decreases with height. So in lower layers, you have stronger field, and then higher layers, you have usually a weaker field. But sometimes you have that, for example, magnetic flux too. It's confined, the magnetic field is confined, but as you get to upper layers, you start to open, to open, to open. Okay. So then these are different special locations. So if you are in this one, you will see a magnetic field that is increasing with height. But if you are in this side, you will be from a region where almost no magnetic field, and then you will cross the magnetic field lines that are opening. So then it will be effectively an atmosphere where the magnetic field is weaker in the lower layers and then suddenly increases. Okay, so it's possible when we are getting to much higher layers, like in this case, to have a magnetic field that along the line of sight is increasing with height. Okay. So, okay, so then I assume everyone did it. So now let's go to the lines file. I think, yes, there's one thing. In the third case, we had all the files in the same folder. Here we will have more files. So we, as default, we assume that we will have where we have the control file, another folder called input. And inside input, we will have different files. We will cover them later. But the idea is that now you see input, and then inside input is where we have the lines file. Okay. You can change it at any time. I will tell you where you can change it. But in principle, by default, we work like this. So inside input, sorry, there's some delay. My computer is much faster. So by default, all those files that are input file, let's say this way, and we put them in input, and then outside this folder, you will have the control file, and then the results of the computation. Okay, but it can be changed if you want. Okay, so then this is the lines file. So if you look at the last part, you will see that they are the same lines that we had last week. And just let's go relatively quickly for what we have. So the first value is the index or the label. So remember that this was just to know how to tell the code that you want this specific spectral line or the other, but it can be changed. So for example, the other day we had like 4 and 5, or 601 and 602, and now they are 6 and 7. Okay. Then we specified with capital letters the element. So we have now iron, but you can see that in the top part we have also calcium. Okay. Then after that there was a number that is for the ionization stage. So 1 is neutral and 2 is single ionized. So now we are going to have also calcium single ionized. The same calcium Han was presenting this morning. Okay. Then the wavelength. Remember this was in Armstrong. Okay. Then after that it's called gamma correction factor. As I said the other day, just leave it as 1. It can be used for modifying the shape of the profile, but this is mainly from cases where the atomic information of your spectral line is not well defined. But in this case, those values for the splitting, the log GF, and sorry, oscillation strength, and all the values, they are well defined. So for now, we just leave it as a 1. But in case you have a new spectral line, you don't find it in the database, you can use the atlas and the code to try to fit the atlas, playing a bit with this value. Okay, but so far just leave it as 1. After that, it's the energy of the lower level. Okay, so in the case of the upper part, you will see a 0, and this is because the first 2 transitions, the lower level is the ground level. Okay, of the calcium line. But in general, most of the cases you have multiple options, and it's essentially you just look for the line, for example, in the NIST database or VALDI database, and just pick the energy of the lower level and you put it there. Okay, in electron volts. Then after that, the oscillator strength, so the log of GF, the product. And then we start with the atomic configuration. In all these cases, again, it's very simple. Everything works under LS coupling. So it's again, the first number is the result of 2s plus 1, where s is the spin. Then we have the notation for the angular momentum. So S, P, D, F, G. So just to get the numbers from there. And then J, the total angular momentum. For the lower level first, then dash, and then the upper level. Okay? And then we have 2 elements that, as I said the other day, we are not going to enter how to compute them, but the concept is if you synthesize the line, you will get a line with a width. If you compare it with the solar observation, and at exactly the same conditions, the line will be a bit narrower. And this is because and there's a lot of theories, but this one is related to the collisions that you have with neutral hydrogen. That is the most the species with higher density in the sun, and this will plot the line itself. So then this is a correction factor that takes into account the solar conditions to make your profile closer to the observed one based on atomic information. This is not instrument or anything. It's just that doing the atomic computation, if you don't include these parameters, the profile will be narrower than the observed one. And then if you do an inversion, then the code will try to add velocities and temperature to make it broader. But intrinsically, the transition should be broader because of these collisions with neutral hydrogen. It's just a correction to make a bit better the synthesis. Okay? Then this is the end for LTE lines. But now we have, if you see up, we have here new things after that. Okay. So then I will try first to explain the concept, and later I will try to show you how you get those numbers. So the idea is, you remember Hans' presentation? For example, for the calcium atom, you had several levels, and the transitions were the interaction between one level and the other. Okay. So then when we are solving one transition, for example, 8542, the calcium line, it's the result of two levels interact, right? So then as we are going to compute the departure coefficients, so how much LTE populations deviate from non-LTE populations, we need to know which levels are involved in the transition. So then what we are telling here, the code is that there's an atom somewhere, and this atom has different levels. And the levels that create that transition, for example, number 5, are level 1 and level 3 of this atom. Okay, so we will have an atom somewhere with a lot of levels, and then we look at this atom and we said, okay, the transition that I'm going to invert is produced between level 5 and 6. Then you go here, and then you put all the information as before, but then you add the lower level and the upper level in that atom. Okay, we will go to the atom later. But the important thing is, if you change the atom and it has different levels, you need to update this file. Otherwise, you will be computing the populations of levels that are not producing your transition. Okay. Any questions in this part? No? Okay, so then just keep that in mind. It's the same as last week, but now we need to also point to an atom level, because it's the one that will compute the non-LTE populations. And we need to specify which levels are generating the transition that we're going to invert. Okay? So if you don't specify any number, then it will be always LTE. If you have the numbers, but you are telling the code that you are not running non-LTE, it will run LTE. Can you repeat the question? Because maybe. Yes. Yes. So all. No, it's the code will know. But the code will do the same. The following. Number 6, it ends like LTE lines, so there's no option for doing non-LTE. Number 5, it has the option for doing non-LTE, but then you can decide if you are going to do non-LTE or LTE. We will tell the code. I will show you later. But the important thing is that only the lines that the lines here, the rows that contain the last 2 indexes can be used as a non-LTE. If you don't have those values, the code automatically will assume that it's LTE. Okay, but we can do the opposite. We can have a non-LTE line treated as a LTE. Okay. You mean if it's possible to solve the iron lines in non-LTE? Yes. You need an iron atom, and you need to go to the atom, look for the index that produced this transition, and then put it here. I will say it again. So right now, we have one calcium atom that we are going to use, but we don't have iron atom. So then the code can only solve the iron transition, solving the Saha-Boltzmann equation. So all the populations are in LTE. But if you want to solve those transitions in non-LTE, you need to create an atom for iron, for neutral iron, with a lot of transitions, with a lot of levels, and then look for the levels that will produce the transition that you have here. I will say it again. If you remember, Han was showing the calcium atom with just a few levels and the hydrogen atom with just a few levels. But then he also showed a magnesium atom with a lot of levels and a lot of transitions, right? So if you have an atom like that, but for iron, that has the levels that generate the transition, for example, 6301, then you can compute the lines in non-LTE. Okay, but for calcium, you need 6-level atom, very, very simple. For iron, you probably need 500 levels or 300 levels. And in general, iron lines, they behave well in LTE. So probably non-LTE is not the best approach for iron lines, or at least this one. Let's say the other way. So why you would like to have non-LTE for iron? Is this for a specific target or? Yes, but these are background opacities. And are you going to talk about background opacities these days? Okay. Okay. So then he will explain a bit in detail, but we are talking about different things here. So when we compute the populations of each level, let's say actively, this is a term that we will use later, it's a different process that when you get background opacities from a series of atoms. You will check it with Han. The idea is that in this case, we are getting background opacities from a long list of atoms, but you are not solving specifically the levels that produce, for example, this transition or the transition, just for calcium. In the case of RH, it's the same. So if you run RH and you solve actively the calcium atom, you will get an accurate spectral line for only the calcium lines. And you will get the continuum for all the spectrum from the UV to the visible and non-red. But you are not solving all the transitions included in all the atoms that you have inside RH. I think I'm confusing you. Han will explain it better tomorrow with RH. But essentially, if you are asking me, is it more accurate to solve iron in LTE with RH than iron in LTE with SER? I would say probably yes, because you are considering a more accurate background opacities. But in this case, we can do the same. So we can solve iron in LTE, but using the background opacities from RH. Okay? But the line is not solved. I mean, the iron lines are not solved in non-LTE as default. Okay? And we'll enter on that tomorrow. And after his class, I will recap this again during the tutorial. But essentially is that. So here we are talking about solving all the populations of all the levels, including one atom. Okay. And do you want to add something, because maybe they are confused or? I don't know if this will help, but I think probably tomorrow he will explain it. But when you solve the non-LTE problem, you solve the statistical equilibrium equations, and then you solve the radiative transfer equation, and you try to make this compatible. So you do several cycles until the populations are compatible with your radiation field. So this is done only for the atoms that we have set as active. Okay, but the background opacities are not included in the iteration of the non-LTE problem. I don't know if this helps, huh? Maybe no. So let's go a bit slower. I will try to get to this tomorrow after Hans' class, and then if it's still this is not clear, I will try to make an example. Okay, but I think what your question is, what your question could be is the best accuracy that we can get for an LTE synthesis, it's from RH compared to SER. I think it's not so different, but I think it could be a bit more accurate because of what we are considering as a background contribution. But in the case of this side, we can use that advantage even if we work in LTE. Okay, but it's different than solving actively an iron atom. It's a different thing. So I will try to explain it better probably tomorrow, but the essential is that. So if you are asking me, can we use this side to get the best LTE synthesis because we are using RH as an input? Yes. Although I'm not sure how much better is, because this is another question. So we can do a test where I do a synthesis with SER, or we can even get the population from SER and from RH, and we can compare a bit. But I think it's probably not so much difference. But still, as we are using RH as a support for the inversion, we can do it. But this is different to what we are doing with calcium. Okay. Let's try, and if not, I will get back to this. Okay. So then let's go to the wave file. As before, this one will be inside input, and we can open. And this case is the same. So I'm now telling the code that I want to solve for, that is calcium 8542, and 6 and 7 that are iron 1 and iron 6301 and 602. So I'm going to compute this one and then these two. Okay. So how about you create your different one, call it different iron lines? I think let's keep the calcium line for now, but maybe try a different photospheric line. So for example, replace 6 and 7 by, for example, 8 and 9 or 10 or 11. So then we can compare later on. Are you following me? Yeah. Okay. Kai? It's just to have another option for comparing when we get results. You can in fact copy the grid file from the SER. So if you had already defined the starting wavelength and the ending wavelength for the spectral lines that you would like to test, just copy it from last week. I will put it here. Just keep the calcium like it is, and then just replace it, and then just play with the value. Okay. So who added 1.5 micron? Think yes, good. How about 6173? Okay, Nancy, good. And how about 50 to 50? Okay, good. So then let me move a bit further. So abundance is the same file, same format. So just keep that in mind. And then we go to the control file. So this one, okay, there's some delay. Oh, sorry. So then if there's some delay, I will also go a bit slower with the script. But so then the control file is here. Now it's called dtrol. I guess desired control file, I guess is the name. So then when you open it, it's essentially what we had before. Okay. So remember, 0 for synthesis, larger values for inversions, -1 for response functions. This is the same. Then in synthesis mode, this is the output. So we are going to feed the code with the Ionosphere, and then we will get as an output the profiles. And we are not going to use any straight line, PSF. And then again, here is what I mentioned. So by default, it's assuming that all those files are in input. But if you want to put them in another place, just change the path there. But just as a default, it's like this. And then this is the atmosphere that each one created with a different value. Now we have this input that we will not touch for now, but it's essentially a way of telling the code that your observation is not at this center. If it's a bit out, you can provide the X and Y coordinates in seconds, and even the Vx and Vy, so the solar rotation velocity in I think in kilometers per second. So it's a file with just 4 values, and you provide there the information. Okay, and for now, just 1 for the Stokes profiles, for the weight for the Stokes parameters, and then the rest is the same, and just few new things at the end. Okay, so let's touch very quickly on them, and later on maybe I can explain them a bit, and then also Han, when he's explaining RH, he will maybe get a bit deeper, because these are commands that we want to specifically pass to RH. But as we wanted to keep everything as simple as possible, we are just using one control file for controlling the SER part and the RH part. Okay, but some things we needed to always provide it to RH. So then the first one is if you want to solve the non-LTE problem. So then 0 means solving it, in the sense that we ask RH to compute atomic populations. And if we put values like 10, then we are telling the code that we are not going to run non-LTE problem. We're going to solve the Saha-Boltzmann equation, and everything will be LTE. Okay. During inversion is a bit different. So I think I will explain it. If not, just remind me, because there you can put different values. And the idea is that we wanted to have the option to tell the code whether we want to have always computing the non-LTE populations or only compute them based on how much the atmosphere changed from one inversion cycle to the other. So imagine that from one inversion cycle to the other, the modifications in temperature, velocity, and magnetic field are very small. So then you can assume that the non-LTE populations are the same. So then there's no need to evaluate again all the non-LTE problems. So then here you can tell if the temperature changes 1%, 10%, 100%, please evaluate the non-LTE problem or not. So it's just a way of making things a bit faster. But for now, during the synthesis, 0, because we want to do non-LTE. Okay, and I will get back to this when we do the inversions in tutorial 4. Okay. Then numbers of rays, I think 3 is a good value. Han will explain. Well, do you want to do it now? Because if not, I will just put all the weight on tomorrow's class.
Yeah.
So 3 is density per incline, middle, and then close to the descent. It's halfway. So then the integration method is referred of how the source function is integrated. I think here it's some kind of legacy, but I would recommend you to use 2, in the sense that with 2, we are telling the code to integrate the source function using the Bezier cubic approximation. And the idea is that RH will also solve. So we have, let's say, like desired part and RH part, and both codes need to solve and compute the source function. So RH as default, as we have configured it, we'll do it in Bezier. So then my recommendation is to always leave there 2, in the sense that also the desired will use the same method for integrating the source function. But in the case of SER, it always uses a polynomial, a Hermite polynomial. So then I think for this reason, you have this as a legacy here, because in the case of SER, the approximation is different. But for LTE lines, fine, this approximation, but probably for chromospheric lines, the Bezier cubic is the best one. So just leave it as a 2, and then will be fine. So then final evaluation of profile, it's for the inversion. So we will check it in tutorial 4. And then whether we want to provide the atmosphere in optical depth or mass column, this is for synthesis. As we are going to do inversions, I'm just putting everything on optical depth. But in principle, if you have a model, that you have in mass column that is sometimes default for RH or default. You can also use it directly here. But in my case, I always work with optical depth because I'm always planning to use it for inversions. But at least the option is there. Okay, so then for now, the important one is this, and this, and this. Okay, so then with that, I think ready. Then we have the RH control files. I think I would like to interact with you. Okay. Yep. Thank you. So then let's just try to run the code. We will interact after coming back, checking the results, and then we will go to RH files, because otherwise I will give you a lot of instructions and then it will be a bit overwhelming. So can you uncomment this line in 387 and just run the script to check if it works? So this is what I get. It said use calling RHF1D, and then it ended just telling one time. So are you getting the same results? Even when you choose different lines and different atmospheres, so everything is working? Okay. So I just wait 1 minute, and if everyone says that it was fine, then we can go for lunch, and you can already have in mind that you have done your first non-LTE synthesis. Okay. Yeah, no problems so far? Good. Lunch? Yeah. Okay. So just as a quick question, is it going well or is too difficult? Oh, is it going? Okay. Because I don't know if it's Monday morning or
Do you want to join us? So I always forget about the Q&A session, but it's supposed to be a Q&A session after lunch every day. And if there's anything you want to address, I mean, I'm sure most of it will be for Carlos and maybe for Han, but any thoughts, any questions, anything that you want to share with everybody, please, this is the time. And if not, we'll move on to Desire again.
Yeah, so
Can you rephrase the question so that everybody can hear it?
Nancy was asking about the three rays, the number of rays, and so let me try to reiterate. So when we solve the statistical equilibrium equation, we need to calculate the radiative rates in each transition that we consider. And to do that, we need to integrate over the line profile, so over wavelength, but also we need to integrate over all angles to get the radiation field coming from all different places in the atmosphere. Right? Now, to do that in an accurate way, people have designed what you call quadratures, which is a distribution of angles that gives you as accurate as possible an integration with as few points as you need. And so, therefore, and you can specify that number, but you cannot specify the individual angles because they're optimized to give an accurate integration over angle, over solid angle, basically. And that's why you just specify the number, but not the individual angles. Because if you would leave that up to the user to just specify angles over which the equation, you might end up with grids that are not as accurate as you can do. So in this case, typically for the one-dimensional case, you use the zeros of a Gauss-Legendre polynomial, which define the set of angles over which you do the integration. That make things more clear?
Yeah. So yeah, not just that, it's what he's saying, that the relation between rays and angle is maybe not direct, but imagine that it's just from here to here. So then 3 is one very inclined, then another like this, another like this. And if you have 5, you will have more in between. But if you have less than 3, you are not covered in like in a symmetric way. So then we have defined 3, but in principle you can define 10 or 20 or more, and it will be covered in this geometry. So from line of sight to very inclined. But the test we did is we demonstrated that between 3 and 5, you are getting good results. Below that, it's not so good. But above that, it makes the solution much slower. But we were not seeing differences in the output profile. So it's essentially that you need to cover all the angles, but in order to make things a bit faster, or RH allows to define specific rays, but essentially they are specific angles in this direction. And 3 will be very inclined in the middle, and then almost 1. Okay, this was, you were, okay.
So this is mostly from Hans' presentation this morning. I'm still a little bit confused on kind of like why, I guess, other than the math being similar, why we actually did the 2-level atom in statistical equilibrium in this case, because yeah, it seems like in terms of the math, it looked a lot like the scattering problem. But other than that, I guess like, yeah, why?
So the 2-level atom is a case where it's basically the simplest case where you can make physical sense for an atom with different transitions, right? And it just happens to be that you can rewrite the equations in exactly the way that you write it for the simple monochromatic scattering problem. And so each of these solutions can learn from the other. Since we've solved this problem with the monochromatic scattering, we can apply the things that we've learned, like this operator splitting method, to the two solutions of the 2-level and by extension the multi-level atom. So it's a way of illustrating. And in early times when computational power was very much limited, 2-level atoms were a way to find solutions for more complicated cases. For instance, Pandora, the radiative transfer code that was used to design the Val models, used what is called an equivalent 2-level atom, where each transition was treated as a 2-level atom, but with additional terms that came from the interactions with other transitions. And so it is a way of splitting out the problem into this easy to understand mechanism that then is applied broader. So the 2-level atom is mostly not because we use it practically anymore, but it's really to understand in the basic, the smallest set of physics that we can apply.
Shall we continue with the tutorial? Yeah.
So can I ask one question? Who of you have already before coming here have worked with the inversion codes, no matter what, Milne Eddington, SIR, or any other inversion code? So it's not that many people. And who has ever solved non-LTE radiative transfer problems? Well, then it's good that we organize this school, right?
problems running the code. So Eleni, and did somebody else have problems? You? Okay. You fix it? Okay. Okay. So just let me explain a bit what could be a problem. And then as we cover files, we will realize why we're doing things this way. So the idea is that in the case of SER, we basically do, not basically, we do LTE. So we don't need many files. We just need the lines file, the grid file, and then the atmosphere. But in the case of RH, you need the atom model, then you need a control file, and then you need a lot of atoms that we use for background, and also a lot of molecules that we use as a background. So then in general, you don't copy all those files in the folder while you're running the code, because otherwise you will be copying a lot of files from folder to folder. So by default in RH, you have these atom models, molecule models, and atmosphere in a given folders, and you run in a given folder, and from there it's always pointing to that folder. So we wanted to do the same with this side. So if you go to, so let's see, let me open one window here, and we had codes, and remember that this side we had these folders, right? And if you remember, we had run, and then inside you can create any folder, and you will call the code from that folder, and it will always look for atoms, molecules, and everything. And this will be located in this folder bar. Okay. So then by default, in a lot of places, we have 2 dot dash, 2 dots dash. So 2 folders behind where you're running the code, there's a folder called bar. And inside there's an atom, molecules, and everything. So then for simplifying the online course, I copy. So here you have bar, and then one folder inside, you have where we are running the code. So I'm pointing always to this bar here. So if you fail to copy this bar 2 folders behind or outside that where you have tutorial 1, you will get an error saying, I cannot find Kurux dot something, I cannot find Atmos, or things like that. Okay. So you can do it in 2 ways. Just copy your folders, new folders while you're running test in dash run inside the side, because there it will always pointing to bar that side. You can copy it like I did. So you have where you're running your codes and then 2 folders above bar, or I can show you all the files where you need to change that. So for example, in the case of input, you go to Atmos. That is something that we will check later. And you can see there's dash 2 dots, dash 2 dash, and then a name. So if you change all these paths in all the files, you can do it in another way. But I don't recommend you to do it, because otherwise you have to do it for every new computation that you do, you need to change that. So then the best thing is to define a folder where bar is somewhere located close to this folder. In this case, or inside beside dash run, because bar is outside, or like I did here. So bar, then you have this side, and then inside this side, you have different folders. So you can do it as you wish. The important thing is that we do it this way because it's like probably between 30 and 40 files, different ones. So bringing those files locally to every run, it's probably not the best option. Okay. So just that. So if you had problems, this could be one of the reasons. If not, we can check it later. Okay. So then we were, okay, so we run the code, and I think we can just check how how the profiles look. And then we will go back to the specific RH files that we need to configure for running the non-LTE synthesis. So let me see if I do this. Then I close this one. Okay, so then this is what I get. Can you do the same? So let the code run until 464. Then let's see if you have something similar. So did everyone got something like this? Okay, so then I want to do an exercise just to allow you to understand things better. So then if you look at this, because this will always happen also in SER, but we didn't do it. So in SER, we just had one spectral range computation. Now we have two. So then when you see this, and if you plot it like this, do you think it's correct or something is off? Okay, yeah. Yes, they are not matching. Yes. So the first thing is that both SER and DECIDE, it will always compute in intervals based on what you are provided in the grid file without really making any distinction. So the first thing is that the left part corresponds to 8542 Armstrong, while the right side, your right side, is 6,300 Armstrong. So in fact, this is swapped. But it's fine. The computation is done independently. It's just that when you do the run, just be aware that this is the first thing. The second one is that you see a jump between the last point of the calcium run and the first point of the iron lines. And this could be due to two things. The first one is that the continuum is not exactly the same between wave and regions. We have visible and the red, but also it could mean that in the computation of the calcium run, we are not reaching the continuum because the line is so broad that the range that we choose is not reaching the continuum. It will not match one, but I would say that in this case, probably if we extend a bit more the wings, we will get even a bit higher continuums. Maybe imagine in this case like 0.78 or something like that. Okay, but these are two things. So you can plot it this way, but we need to do some arrangement to properly plot this. Okay, so then before going to your profiles, let's try to do it intuitively. So sorry, let's practice. So then I remove this one, and now what I'm going to do is I'm going to do the same plot. There's a stop here, but I will add the wave information. Okay, so then I do this. Let's let me comment temperature 1 second. It's not. One. Okay, go back. We want to have this one and then this one. Okay, so now this, and we said, okay, this is not correct because I'm just plotting stocks high. So I want to plot wave and stocks high. And then I get this. That probably you can say that it's not getting better. And this is because again, the wave file, it's always centered on the line core of the line of each entrance on the wave grid. So we have from minus 4,000 to 4,000 wavelength vector to calcium for calcium, and then from minus, I don't remember, 700 to 1,000 something for the iron lines. So then it's plotting just them on top of each other and connecting the last point from calcium to the one in iron. So then I prepared here very simple instruction. Probably I think someone already did that last week, but essentially what I recommend you to do is comment here and then comment here. So what I recommend you to do is to extract information from the index, that is the first column of the profile sort pair, and then separate in different arrays. So you have index 4 for calcium and index 6 for iron. So then you can do 2 plots. In this case, you can check this later, but essentially I'm just separating between the two spectral lines. And here I'm just defining them in this way to make it easier to understand. And then here we have the next step. So in this case, I'm just plotting now the 4 stocks profiles for calcium. Okay, so I just went to the profiles file. I looked for index 4, that is the one associated to calcium, and then I just pick those values. And then I'm plotting the wavelength file for all the values with index 4. I'm plotting stocks I, stocks Q, stocks U, and stocks V for all the index, all the pixels, and related to index 4. Okay. Okay. So far, so good. Okay. So now I'm going to just show you also the iron lines in the same way, and then we will go back. We will check your profiles, and then just to check that it looks like this, and also with for the iron lines. And then we will discuss a bit differences that we see in the stocks I, Q, U, and V for these profiles or your profiles. Okay. Okay, so then let's go back. And I think, let me run from here until the next one. Oh, no, sorry, no. Then let me show you, let me see your profiles, because we will do a zoom of the line core of the calcium line. So then just before that, let me see your results until this line, so 464. So we know that in this case, the results are not, sorry, because I need to, the results are not strictly correct because we are just putting one after the other, but I just want to see your stocks I profiles based on different spectral lines and different initial atmosphere. Okay, so just let it run until 464, and then let's check stocks I. Okay, so just let me know when you're ready. Nancy, ready? So can you show us 6173? Okay, I will stop sharing. Yeah, I think Nancy was trying. Yeah, Nancy was connecting, but so who is connected now? Nancy? Okay, 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 okay. Then later after that, Vincent. So then I think you have strong magnetic field, as you said. So now we see the splitting, and then probably some velocities, right? Because we are seeing some effect here, and it's not in the other side of the line. So probably this is velocity. Okay. A gradient. Okay. Okay, good. And yeah. Good, good. So then again, we have that this is probably either not reaching the continuum, or it also due to the difference between 8,000 Armstrong and 6,000 Armstrong. Okay, because the continuum is slightly changing. It's slightly getting slower, lower with wavelength. Okay, Vincent, you had a really strong magnetic field. Good, good. I think it's too much. So then here we are seeing something interesting. Of course, the splitting is really nice, but I think it's really a lot. But one important thing, and probably Han will explain this a bit this week, is that the calcium line, although we are seeing some, I think it's numerical error here, it's going to be very, very difficult to see Zeeman splitting in the calcium line because it's really broad line, and the Landé factor is also very small. So it's going to be really tough to have a magnetic field that produces splitting that is detected in the calcium line. And at the same time, this also helps for applying weak field approximation for calcium line, because in general, it will be valid. So do you want to say something?
Yeah, so ratio segment.
So I think, I'm not sure what is that, probably numerical error, but because it's very, there's some small things, but in general, it should be just smooth. So this is interesting. So if you look at the calcium lines, in general, you will not see splitting. And this is because what Han is saying. So in this case, we have a different sampling because the sampling, I think, is 20 milliarmstrong, and we have like, I think 200. So I think minus 4,000 to 4,000 milliarmstrong, and we still are not covering the line. While for photospheric lines, usually with a normal one, it's minus 500 to 500, we are covering the line. So these lines are much, much broader. Okay. But it's good. Let's keep this. And I don't know what will happen with this, but let's keep it. And then let's see how the inversion behaves in tutorial 4. So then, thank you. And then 1.5 micron, do you have it? Yeah. Okay, good. So we have that the line is completely split, but in this case, as you remember, the line is in the infrared and it's very sensitive to the magnetic field. So this means that the field is strong, but essentially after 700, 800 grams, you will see this. So how strong is your field? $200. Okay, good. And then some velocities, yeah. So it's not always easy to understand what are the spectral signatures of the atmospheric parameters, but in general, when you see this type of changes, and usually in one side of the line, it's usually some gradient along the line side, most of the time velocity. So you can start getting a feeling of, if you see this, then you should definitely add gradient during the inversion. You cannot try a constant line of sight velocity magnetic field. Okay, so then how about 50 to 50.2? Do you have it? Yeah, okay. Good. So then we are seeing an even larger jump because we are even up to the blue, so with 50 to 50. And then in this case, I think we are seeing temperature, right? Did you check the temperature? Yeah, so it's hotter. Yeah, so then we are not seeing, so this is not the effect of strong magnetic field, it's probably temperature that is, this line is very sensitive to the magnetic field. So as soon as you increase a bit, it's getting hotter, then the lines becomes much narrower. Okay, but this line is very good for understanding the temperature variation of the solar features. And then this looks reasonably well. I think some effect here, so probably some gradient. We have gradients or just no constant. Okay, so maybe the temperature that is changing this is also affecting here. So it's going to be interesting to see how the code inverts this. Okay, good. Thank you. So shall we continue, or does anyone wants to show the results? I think we can do it later also with when we add noise. Okay, then just let me share my screen. And then what I was saying before moving, so I did the separation that in your case, depending on the index that you use, you have to define a different number, but in principle, you can also split the chromospheric part from index 4 and the other index that you had. And then I said, let me show you this one. This one. Second. This one. This one. Okay. Where am I? Okay. Okay. So then we see, just let me remove this one. Second. Out. Okay. So now we can check yours. So let me as well. So then now let it go until 602. So then there, oh, a lot of things here. Yeah. So this is how full Stokes profiles look for the photospheric lines. Okay. In my case, very simple. Sorry. I jumped. What is this? Sorry, let's go back 1 second. I went too fast. I wanted to discuss with you the Stokes profiles for the calcium line. So then let me see this one. And then I will comment this just to avoid. This is out. Out. That's fine. So then we are stopping in 577. Okay. So then here, what I wanted to show you is that we were already saying that the line is very broad in comparison with photospheric lines. But then if you look at the Stokes profiles, they basically don't have signal in this part. So it's very broad, but essentially the main contribution to the polarization signals come from the main line core. Okay, we will see this in response function. But essentially you see that it's almost zero, then it starts to get something. So we get, in this case, some signal from the wings, and then we get a big jump from the line core. Okay? And then we can continue to the next one. Now we stop in under 2. Okay. In my case, it's very easy because it's a flat, so a constant magnetic field, so everything is symmetric, and it's relatively strong and vertical. Okay, so you can check yours. I don't know if you want to show them or just go a bit ahead. Shall we proceed? Let's go ahead, and then we can check them when we add noise. So then what I do here, oh, I think I jumped one notch. 1 second. No, I make it later. Okay, so then we are finishing this part. I put a lot of questions, but I think that's fine. Yes, and then, oh, sorry, we jumped the RH files. Yeah. Sorry. Okay, so now the code run. We saw that we have profiles. We saw that calcium is much broader than the other lines. So for this reason, we have much more larger wavelength range. Now, let's go to a not so interesting part. I will go fast because I don't want you to fall asleep. So, so we have that in tutorial 1, we have synthesis.trol, that is a control file, a master control file for decide, and is similar to SER. But then we have keyword.input. Okay, so this is the master file for RH. It has a lot of options, but we try to minimize those options and keep most of them fixed. So my recommendation is that you can look at it, you can check RH manual, but for most of the cases that we are going to cover here, you don't need to change it. The only important thing is that just to get an idea, we are specifying in input. Remember that we have a folder input. So we are specifying in input where the atoms and the molecules input file is. So imagine this as a grid, as the wave grid. So you had lines, and then through the wave.grid, you told the code which lines you want to synthesize. So then this atmos.input is going to tell the code which atoms we are going to solve actively or which ones passively. So it's a way of telling from all the options that we have, which ones we want to have as a active atom for the non-LTE solution, and the same for molecules. Then the code needs to do iterations to solve the problem. So solving the statistical equilibrium equation, then check that this is compatible with the radiative transfer solution, then compute the emerging intensity, and then repeat the process. So this is the number of iterations that we are telling the code to do as a maximum number with accuracy of this value. So it doesn't make sense for you now. I think Han will explain a bit about RH tomorrow, but if not, check the online tutorial because we covered this in detail. But essentially, we need to iterate for the non-LTE problem. Besides the inversions, for the non-LTE problem, we need to iterate, and we are telling the code the information regarding this iteration here. The rest of the things, just leave it like this. And if you want to change them, just contact me because I can help you. But for now, just leave it like this. Okay? And just keep in mind that this is the master file for RH. Okay? Then if we go to input, we will have abundance, and then we will have this file. And this is similar to the grid file, but instead of referring to spectral lines, it's referring to atoms. So we have large library of atoms. Okay, so each file will have a series of levels, a series of transitions, the probability of the transitions, and a lot of information. And in this case, we are telling the code that we want to use those atoms for computing background opacities, except in the case of calcium, that we want to solve as active atoms. That means the code will solve the statistical equilibrium equations, computing the populations for the levels included in this atom. Okay, but not for the others. And if you see, I change this and I put the atom inside input. And this is because for our specific needs, we are going to change some information inside the atom. So what I always do is that if I'm interested on analyzing a sodium line, I copy the sodium atom in the folder where I'm running, and I leave the standard one in the bar folder that is there. And then this is the only one I change. I keep the other as default, because you can really affect modify the results you get from the atom, changing the parameters inside. So the one that I'm going to modify, I copy it locally and leave the others like this, and I point to this one. Okay. And the idea is that active means solving it, so including it in the non-LTE solution. And if you put passive, then it will be, everything will be LTE. Okay. So then we have also molecules. In this case, in general, it's always passive. We don't solve molecules actively. So it's just that we get a more accurate background opacities if we include all these models. Okay. And then we have, this is what I said before, it's just 4 points, just for X, Y, Vx and Vy, we just leave it there. And then the grid is the same. And then we have one atom, but as I said, this is the one that I copied from the standard library and I change it, okay? And the idea is, it has some information, these are levels, and these are transitions, okay? So when you are solving a transition in RH, that in this case is similar, you can tell the code how many points you want to have along the line. Similar to the wave grid file, we can do the same for RH. So you can tell how far from the line center, how much density of points and things like that. So then these are the values that you can have here, here, and here. I think Han will explain them, but essentially, when I copied the file from the library, I changed those values. I tested that they were reasonably fine for the example that we want to run, and then I leave it locally. Okay. And I wanted to say something, and yes, so even if you don't understand the atom, before we said for the wave grid file, you need to provide the index of the levels involved in the transition. Okay, so then in this case, we write with comments that this is the infrared triplet, and this transition, sorry, this one, 8542, is a transition from level 4 to level 2. Okay, so if you go to the grid file, sorry, the lines file, yeah, you have that is from level 2 to 4. We are writing in the grid file from lower level to upper level, even if in the atom file it's this way. Okay, so this is the only elements you need to know when you use an atom. So even if you didn't create the atom, someone gave it to you, just check this index, and these one are the ones that you need to have here. Sorry. Okay. Because if you change this, imagine that you put 2, 5, you go here, that's not 5, but imagine 4, 3, then you are computing the atomic population for a transition that doesn't exist, and it's not the one that you are solving. Okay, so just be aware of that. These are the only numbers that you always need to double check if you add a new atom. Luckily, there's no many atoms, so you will not be able to go to a library and get different atoms. There's only just a few models, and it's relatively difficult to create them. So in general, most of them are already in the library. Okay, but if you create one, just be aware of this. Okay. Then I think that's all regarding RH files. Yes. So then let me close things here. And then I put it something at the end that I think is interesting. So I'm going to do a test. The characters are a bit large, so it takes time. Okay, so this is what we get. Okay, this is what we get when we run calcium as an active atom. Okay, so then if you go back, and let's put here 10. Okay, then we run. Oh, let's try again. No, it's not. Yeah, sorry. Yeah, so 10 here, and I'm not calling this side, right? Yes, thank you. Okay, so definitely is wrong. I think Han probably will explain a bit more about this tomorrow, but essentially, if you are going to treat chromospheric lines with this side, be sure that the atom is active and you are calling RH, because with LTE populations, you get wrong results. Okay. So the photospheric lines are fine. They are the same. That is the calcium one that is wrong. Okay. Yeah. Okay. Okay, so then I will put this back to 0. And in your case, just let it run until the end, until you write the profile. No, just let it run. So you already did it. So in your case, everyone has a profile subpair in the folder, right? So then we can move now to tutorial 2 and add noise to the profiles. Okay. Okay. Tutorial 2. We can open it. Okay. I think this is much more complex than SER. Are you following me or I'm confusing you? Is it okay? Yeah? Yeah? Okay, so then this one is very simple. It's the same as before. We add noise to the profile and just save it. You can choose if you want to use a different noise. And the idea is that it's the same. So we read profiles from tutorial 1. Okay. We have them here. And then we compute how many wavelength points we have. And we are going to add a noise with this amplitude. In general, it may happen that if we are observing 2 wavelength regions, like in our case, so one 1,000, the other in 5,000, and you're using, for example, 2 cameras, you may have slightly different noise levels. Can happen, but for simplicity, let's compute one random noise for all the pixels and just add it. And then this will be our final profile. Okay, so this will be like this. And then in my case, just let it run. So okay, this will be the noise that I will add. And then it will look like this. Okay, so in this case, I'm plotting all together. Before we just show stock high, but I wanted to have it here first to check how the noise affects the profiles, but also because in this plot, you can see something that it will be always present. And it's just when you are, in our case, we are using, let's say, good photospheric lines or the best for polarimetry. And calcium is also the best for chromospheric polarimetry. But you will see that in all the cases, except some specific scenarios, you will, in general, will have much larger amplitude in the polarization signals from the photospheric line than the chromospheric lines. Basically, because as Hans said before, it will depend on the Doppler width. So these lines are much wider than these two. And also, the lambda factor of the lines that we are using, for example, this one, it's twice than the other line. So just because of lambda factor Doppler width, we are always getting much more signals from here. Or another way around, chromospheric signals are going to be a challenge for observation. Okay? So if you want to make a map of a chromospheric, for example, 8542 in the quiet zone, you really need to have a high signal to noise ratio. Otherwise, you will essentially will have noise. Okay? So then, can we see your profiles? Yeah. So about C173, 5250, and 1.5 micron. As soon as you have it already, 1.5 micron. Okay. Okay. So interesting. So it's this we saw before, but this we didn't see it. So it looks very nice. And as I said before, we will have much larger signals, but also they are going to be it's a different shape. So this one, it looks like it's smooth. And then here we have like a jump. So it's going to be interesting. You will see that signals from chromospheric lines are a bit more challenging to model. And here is very interesting because I think the magnetic field is decreasing with height. So it's not only that, as I said before, you will have less signals for the same magnetic field. You will have less signals in the chromosphere than in the photosphere. But in this case, the magnetic field is decreasing. That is reasonable. So then you will have much larger signals here than here. That is noise. This is, yeah.
Different than the blue component. It's asymmetric. Why is that so?
Because he added a line of sight gradient in velocity and magnetic field. So
the magnetic field would still result in a symmetric.
Yeah, but velocity.
But the velocity is what causes this skew.
I think so.
The line of
the
component.
So.
Okay.
Yeah. So someone ask something here? No. Yeah, I think Jana is that. So if you have flat line of sight velocity is completely asymmetric. But as soon as you start adding gradients, you will see this effect. Yeah. Yes. So you have this bandit. So then in this case, I think is velocity the main driver. Yeah. Yeah. Oh, so it's crossing zero. Okay, good. Let's see how the code handles that. Okay, so then how about 6173 over there? Yeah. Okay. Then that is very good because I think you said 85 degrees inclination, right? So then, or 87. Okay. So then the magnetic field is so large that still we have Stokes V, but if you compare how large is the noise here in comparison with here, you have a lot of Q and U signals, and we are seeing these strange phenomena. I think it's the magneto-optical effects because the field is so large that probably they are dominating there, but Q and U signals are very nice, and again. It's in this case the shape is similar, but still signals are much weaker. Good. Yeah, thank you. So then 50 to 50. Yeah. Okay. Good. So then I think here we have some interesting things. So first, that again, signals are much larger for photospheric lines. In fact, this is basically noise, while here you have a lot. And then here they are okay, but still you see like factor 2. But I think this atmosphere is interesting because the 50 to 50 line, 50 to 50.2, it's a line with a Landé factor of 3 that in the visible is the largest one. I think there are another 2 lines with Landé factor 3, but they are relatively narrower, so they are not the best. But this one is deep and with a large Landé factor, so then it's one of the best candidates for having large signals even in the white sun. But it's also very sensitive to temperature as well. So in this case, as you are having like a hotter atmosphere, it's getting narrower. So then the signals here are a bit lower than the line close to it, even if this line is less sensitive to the magnetic field. And this is because the line is getting narrower due to the sensitivity to the temperature. So then the line is good, but sometimes when the temperature is a bit different, like very cool, it will get very dark and the signals will be very large. But as soon as you get to a bright point or to a hot region, then it will get almost flat, and then this will impact the amplitude. Even if it's still sensitive to the magnetic field, the amplitude of the signals will be reduced because the intensity itself is also reduced. So this line is interesting, but sometimes it could be a bit tricky to deal with it. Okay. So just be aware of that. So temperature will always have an impact somehow, even in the polarization profiles. Okay. Solution, does it sound good? Or you yeah? Okay. Questions? No? No? Good. Okay, so I think we covered all of the lines. Yeah. So shall we jump to tutorial 3? Okay. Close this. Just as a reminder, so I put here the stop in 102. Just remove it and let it run until 119. So you get the right profile for your configuration. Okay. And then, okay, that's fine. So then we go to tutorial 3. Let me close this one, this one. So is it time for a break or can I continue, Rebecca? Yeah. I think we can break now. Yeah, before starting tutorial 3, and this will be fast, in fact, but let's break. Yeah. So again, is it going well? Because I feel that participation is like a bit lower than last week. I'm tired as well, but maybe. So is it going well? Okay, good. Do you remember what 3 factors were important when defining the atmosphere? First one was that the number of nodes that you can allocate during the inversion depends on the number of optical depth points your atmosphere has. Okay. Second one was you have to have an atmosphere that is wider or it has points for deeper and higher layers than the height of formation of your spectral lines, but not much higher or much lower. So we need to find an interval where the spectral lines form, but the response functions are able to fall, but not much longer than that. And then the third point was, if you plan to embed an atmospheric parameter, then your initial atmosphere should have non-zero values on this atmospheric parameter. Okay, so if you plan to embed a line of sight velocity, it cannot be 0. I think one case last week, and someone tried and it complained. So I think the code will stop, but just in case, be certain that if you want to embed macro, micro, line of sight velocity, magnetic field, just put values there. It could be large values, or it could be small values. Okay. So then with these 3 things in mind, let's create an atmosphere. Again, we did the synthesis from HSRA, or the thermal part of HSRA, adding the magnetic configuration and the line of sight velocity you consider interesting. And now we are going to start from a FAL model that it has a different thermal part, and we will add different values for magnetic field, inclination, azimuth, and everything. But in this case, a bit easier, because as I said last week, this model is already optimized with a number of points that are good for chromospheric inversions. So we have 81 points, and it goes from 1 to -7. Okay, so can you quickly run the script and tell me what are the nodes that we can use with 81 points? You can put the stop at the beginning and just write nodes, and just tell me which are the nodes we can use until like 9. Okay, did you get it? Which values? Yes, 81. Okay, so then 1, 2, 3, 5, 6. Okay. So then just have this in mind for tutorial 4, where we are going to do the inversions. 1, 2, 3, 5, 6. Basically, with this, we are covered for normal cases, but just be aware that 4 is not allowed with this number, but essentially between 3 and 5 is a good jump. You don't need to have 4. And I forgot to show you this. This is from the manual. This is a way of seeing how nodes are distributed. So you can see that one node is just complete perturbation up or lower, for example, in this case, temperature. Then two nodes, they are always located in the streamer, bottom and top of the atmosphere. Then three is just one in the middle, plus the top at the bottom. And then it just goes this way, always equidistant between each other. And then, for example, in 8, it will be like this. Okay. This is inside tutorial 3 in HD figures. Okay. So then let's, in your case, so you can go to line from 144 to 149. You can choose these values, or you can change a bit. And these are the values that, so the atmosphere that we will use for initializing tutorial 4. But as always, depending a bit on your initial atmosphere, you can get slightly different results. But I recommend you to have mild values. So velocities small, you can I think Vincent is already putting 10 kilometers and maybe 5 kilogauss. Yeah, for initializing it should be simple, but sometimes you can run with 3 atmospheres or 2 atmospheres, one with a positive velocity and the second one with a negative velocity, one with a polarity below 90 degrees, and the other with an inclination above 90 degrees that will produce opposite Stokes polarities. This can help, and this we do in parallel. So in the future, when you get to do parallel inversions, I will show you how to create atmospheres in different combinations, so you can get a varied range of initial atmospheres. Okay, but for this case, just pick one. It can be the same or a different one. And then just let the code run until 159. So your initial atmosphere is saved. Okay. So when you're ready, let's move to tutorial 4. Yeah. Then I think here is better specified. So in your case, your tutorial 4 folder, you need to copy the noisy profiles that you generated in tutorial 2. Then the initial atmosphere that you generated in tutorial 3. And then the files that you use in the folder input inside tutorial 1. So your wave grid and the rest of the files, I think they are all the same, but at least the wave grid is probably different. And then just put this inside input in tutorial 4. Did you do it? So can you run? I think this line was commented. So can you run until this line 41, but including the command for running the inversion? I will run it also here as well. So how was it? Did you get something like this? So now I think you probably noticed that it was slower, right, than Sarah. So it took some time between cycles, but still fast in the sense that you have already done non-LTE inversion, and it took like 5 seconds in your laptop. So it's fast, but it's not 1 second or maybe less than that as in Sarah. But still, we are really, really fast. Okay. Oh. Did you have it? But for all of you, did it work? What are you saying? Are you checking the times? Yes, yes, yes. So how is in your case? Twice. Okay, okay, okay. Twice. Yeah. This is for 2015. 2013. Yeah, yeah. I like it. So this one has ports like Ethernet and other things that I miss these days. Yes, yes, just in case. I like it. Like, okay, so then complete it. Okay, so then we are going to do the same as in the previous tutorials. So we run inversion, we check the results, and then we go to the configuration files, and line by line, we check how we define things, and then we will probably experiment a bit. But for now, just we go from here. We are not going to run it again because the results will be the same. And then I know that we are going to, so we did only 2 cycles. So I'm going to read 2 cycles. I'm already separating in the calcium and the iron wavelength regions, and I'm going to plot calcium. Okay. So this is what I got. So I was confused in the previous one. So in this tutorial is where we're going to do zoom. So the idea is that if you look at this, you will say this is great, right? Because the results for stocks I are very good. For stocks B, it also seems very good. So red, that is a fitted profile, and dark, that is the input. They are basically matching each other. And stocks Q and U, they are okay, but they are very noisy. So it's still, I would say that is nice. But the problem is that for chromospheric lines, the core is very narrow in comparison with all the line. So I always recommend you to make this plot just to get an idea, but then make another one where you make zoom of the line core. And this is what I do in the next plot. This is what I was thinking I was doing in the previous tutorial, but it's here where I do it. So then if you let it go until 129, then jump this one, and then this is what we have. So for chromospheric lines, always also check the line core, because it's very different. Because as Han was saying today, you get that the line goes like this, and then it gets very steep in the line core. So there things are a bit different, and it's important to check that not only you're getting the far wings, but also the core. That is essentially where you have the main contribution to stocks Q, U, and V. So in this case, again, it looks fine. I would say I like the fit, mainly stocks B looks, well, stocks I definitely, but then stocks B in general, we have this behavior with this. In fact, here is trying to do this jump, And then here the amplitude difference are okay, they are reasonable. And then, yeah, here is more or less. Here we are not so good. But again, this is 1, and here we have around 4. So then the errors here are probably in the same order than here. But here the amplitude is much larger. So I would say that it's fine. It's a good fit. Okay. So then let's try your case. So I think probably it's fine the plot with the full range, such as in your case, run the inversion once, then comment the line, and then let it go until 129. And then let's check how good is the fit for calcium, but for your atmospheres, okay, that are different than the one I use. Something? Did you guys? Okay. Yeah. Not good. Okay, let's see it. Yeah. That's good. Otherwise, we are going to finish the tutorial today, and tomorrow we we don't have to come. Okay, good, good. So definitely something is off. That it's fine. We are seeing that the wings are fine. So, but I don't know why it's doing this. And then, of course, as it is doing this wrong, then it affects to all the profiles. So then I know that we are only running, I think, 2 cycles. So probably this is definitely not enough for chromospheric lines. So now the next exercise will be, let's play to get this better, but let's check other fits just to see if we have similar problems. Because I'm using, I think, a very simple configuration, but suitable mainly for photospheric lines. So now we need to add a bit more freedom and play a bit. So how about here? In your case, you have a bit hotter temperature. Did it fit well or also wrong? Fits pretty well? Okay. So can you show it to us? Let's do, yeah. Yeah, it's fine. So who else? Yes, sorry. Okay, yeah, great. So the intensity is very nice. Small error here, but I would say that it's fine. And then Stocksby looks very good. So can you let it go to the next plot? Just because this is the first plot. This is in line, I don't remember. But if you continue, I make a zoom of the line core. So it's the next plot after that. It will be just plotting the line core region. So I think it's the next one. Yeah, I think 169. Yeah, this one. Yes, this one. Yes. 129. Yes. Yeah. So yeah, yeah. So again, in fact, this one here we have this bump and then this bump here. But I think it's signal, it's not the noise, and the code is doing it. So I think it's great. And then this is what we saw before, that the line core is not perfectly fit, but it's really good. And then small error here. So I think that's probably fine. And then the Stokes Q and U signals, even the noise is very important. I think the fits are really good. Great, thank you. So then besides Nancy, who had really wrong fits? Okay, Vincent, can you show it to us, Vincent? Yeah. Okay. Okay, good. I don't know what the code is doing there, so I think we may need to increase the nodes, but maybe we also need to change the initial atmosphere. So we will experiment until we get this done. So because in this case the field strength is large, but it's constant with height, and the line of sight velocity is also constant with height. So no complex pattern. Okay, so then it should work, but maybe we need to start from a different atmosphere. Yeah, okay. So then another one. So in your case, you also said that your results were not good. Can you share it with us? Okay, it's fine. Okay, so you're ready. Okay, so then if you are already trying 3 cycles, just remember that you need to change the profile that you read. Okay, so if you go to line 47, this case, it's assuming 2 cycles. So if you run 3 cycles, then you just put here -3. Okay. Yeah, okay, perfect. Yeah, close. Okay, yep. So something is wrong in temperature because the continuum is not so good. And also the line, like, it's not trying to make this shape here. So probably temperatures are off. And the magnetic field is not so bad, but still we are not making this shape here. And I think it's because we are not matching this one here. So then in this case, maybe the nodes are not the problem, it's maybe the weights. So we are maybe even more weights to Q and U or something like that. And then the code is just getting confused. So maybe you can stop sharing, and maybe you can try to repeat exactly the same, but changing the weights. And let's see if this improves. Yeah, Kurt, yeah. Okay, yeah, interesting. Yeah. Yes. Okay. Okay, so this is already 3 cycles. Okay. 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 Yes. Yeah, so I think here Stokes is getting there in the sense that this part is well, but then I think it's getting confused with temperature, probably, and then it's not fitting well, wings and here. So then let me see. So in your control file, you have 235 for temperature. So can you show it? And now we can change it now. So yeah, well, yes, inversion detrol, and then I think okay. So maybe try to put maybe 2 in the weight for Stokes P, and just give it a try like this, maybe. Yeah, just to test if improving Stokes I will eventually improve the results of the others. No. Um, Sorry. Okay. Okay, that's much better. So I think now we may play a bit with the weights because I think it's getting there. Maybe here it's missing something. We can add more nodes to temperature, maybe another cycle. But now it's getting here. At least it's not doing the crazy jumps before. So it could be a bit strange that putting more weight in the stocks I helps you in the stocks Q, U, and B. But we always have to think that mainly in the stocks B, it's related, it's the derivative of stocks I. So sometimes it's the opposite. You need to put stocks Q, U, and B, but sometimes you can do it the other way around. So I want to have better fits here, and then eventually this will also follow. So in this case, I would say that you can try just or either another cycle with more nodes in temperature mainly, like 2, 3, 5, 6. And then if this improves, then you can leave it like this. If not, come back and then change the weights. But you can just stop sharing, so just do it, just play a bit. Because this is what I wanted to do last week, but I knew that with SER is not so easy to get to this point where just a few changes really move to bad fits to good fits. But I think now we are getting there. So someone else with bad results? No? Yeah, Simon? Yeah. Okay. Yeah, no, you're ready. Okay, so then I go to another person. Yeah. Okay, Vincent, did you get better results? Okay, so can you share it with us and also tell us what was? Mm-hmm. Okay. Okay. So then in this case is so your atmosphere, the one that you use for the synthesis has a weaker magnetic field. Okay. 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 So the truth is that if you look at the sun, usually 3000 Gauss is compatible with cool atmospheres, and so having HSRA temperature that is quite sun plus 3000 Gauss is not, I think, not possible. So maybe the code was not able to do it, but now it's much better, right? Okay, okay. Then someone else? Yeah, Tushan. Yeah. I think they are multiplicative factor. So weight 2 is 2 times the other. So if you have 1112, then the chi-square. So the difference between imagine I, Q, U, and V. So 1112. So then the results from the difference between V original and the V fitted will be multiplied by 2. So the difference will be twice larger. It's just a multiplicative factor. I think it's like that. So then it means that if you want that a different stocks B, it's more important for the code than the stocks Q, because you feel that it should be this way, then just change the weight and then it will go just linearly. Okay. So, yeah. Yes. Yes. Yeah. Okay. Yeah. So are you sure that you brought the correct? Okay. 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 So yeah, because it's so I'm not sure about that. So maybe it's just that we need to play with the number of iterations and with the weights, because definitely this doesn't look like this one, but the wings, they look fine. So I would say that we need to change the configuration and to change the weights probably, but just double check that you are bringing the correct profiles. And if yes, then add one cycle, add in 5 nodes of temperature, and then 3 and 3 for velocity and field strength. That is what is by default in the file. And then try to run it again. And then after that, just tell us so you can stop sharing. Rebecca, is it time to stop now? Yeah. Yeah. Yes. Yeah. So I think we have 2 options. I would say that now after that, I will try to show some plots, but I will not go to tutorial 5 because in fact, I think we are going fast today. So we will finish earlier, but I don't know if you prefer to just continue and then finish earlier or to have a break and then a very short part after the break. What is it better for you? To just maybe 20, 25 minutes more and then stop for today? Is it better? Okay, so then let's move on because so we have seen this plot. Yes. So let's move here. And then let's stop 1 second here. And I think tomorrow we can start checking your profiles. So I guess that now we are saying, okay, the fits is good or bad, but we are talking about calcium only. Okay. But you also need to check the other set of lines. And this is important because if you had the same relative error between the fits of the calcium and the fits of the iron lines, the fits for the iron lines are much worse because the amplitude is much larger. So you need to be sure that at least you get right the photospheric lines and then to try to get the best for chromospheric lines. But don't forget to fit these lines because in my case, for example, this is like 3 times larger than the calcium fits. So in this case, it's also good. But those of you that were checking what I get with 3 cycles and weights, now you also need to check that you're still getting good results for the iron lines. So as we are getting a good pace, tomorrow we will play with an additional option that is, I think you can use it in CERT, but essentially it really makes sense for design. And the idea is, so far, we are using weights or telling the code that even if some Stokes parameter has weaker signals, we want to get good fits because otherwise we will not get a good inclination, a good azimuth, or a good field strength. So then we know that we are playing with the difference of amplitude because we know that we want to get good results for Q, U, or V. But now, and I was saying before, almost always the signals for the photospheric lines will be larger than the signals for the chromospheric lines. So the code will use the chi-square value for the complete wavelength range, and then Stokes-P signals, for example, from photospheric lines, will in generally weight more than the Stokes-P signals for calcium lines because they are weaker. So tomorrow we will learn how to provide wavelength-dependent weights. So if you want to tell the code, I know that the Stokes-P signals from calcium are weaker than the Stokes-P signals from iron, but I want to fit that with high accuracy. So weight them in the chi-square twice larger, 3 times larger, 5 times larger. Okay, so this is an extra addition. In the case of SER, it doesn't make too much sense because the difference of amplitude is basically the Landé factor, so then it usually works well. But in this case, the chromospheric lines usually they are less sensitive to magnetic field, they are broader, and they also form in regions where the magnetic field tend to be weaker than in the photosphere. So then we added this extra option. It's really complex to make it work, but at least I will teach you how to use it. And for example, in the Desire paper, if you take a look at it, we embedded this configuration, so 6301, 6302 plus calcium, and there we put twice weight in the calcium polarization signals than in the photospheric lines, and it produced much better results. Okay, so the option will be there. I will teach you how to use it, and then making it work, it can require some trial and error, but at least you know that it's an option that you can use. Mainly because here it makes sense in the sense that they are weaker in general, but if you don't fit well the Stokes-P signals in calcium, you are not getting the magnetic field in upper layers, right? Let me say again, the line core for calcium line is sensitive to upper layers. So the Stokes-P signals that you see from calcium line, they are essentially from upper layers in the atmosphere. So if you do get that wrong, then you are fitting Stokes-P a bit worse, but you are getting worse magnetic field in upper layers, not in the lower part. That it could happen, for example, with SER. If one line is worse than the other, you are not getting a good stratification between 0 and -2. But now we are talking about -5. Okay, so then we will cover this tomorrow. Okay, so then just check this. We will start tomorrow checking this, but just let me go very quickly to the control file, and then tomorrow we will continue from this point, 166. So I think I'm really happy to see that you already said, I want to change the number of cycles, I want to change waves, and you're already doing this. And I'm excited because this is a different code than SER, but we try to keep it as compatible as possible. So then if you learn how to use Desire, you already know how to use SER, and the opposite. So you get 2 for the price of 1. That is, I think, a good deal. But there are some things at the end, as we said before, and in particular, this one. Okay. So here, let me explain you again what this means. And here we are telling the code. 0 means that in every inversion cycle, here I have 2. We call RH, we solve the non-LTE populations for calcium, we use them for computing the departure coefficients, and we evaluate the profile. Now I'm putting 0.1. So what I'm telling the code is, if between cycle 1 and 2, the temperature in any position doesn't change more than 10%, don't call RH, use the previous non-LTE populations. If it changes, then use it. So then what I'm saying is, if for any reason the changes in temperature are not so big, we are increasing the speed at the level of SER. So if we are not calling RH, we are just as fast as with SER. If we are calling RH, we are a bit slower. But if you have like 5 cycles, it may happen that you need to call RH only 2 times, only twice. So then this is improving the speed a lot. So we are faster because we are using the departure coefficient. But at the same time, we are even faster if we are moving in this context. And then it's up to you to decide which value is okay. I think 10% is a bit demanding, but I prefer to be in the conservative side. But you can move this, for example, like 0.2, 0.3, and it will be even more relaxed. Or if you said, no, I'm not in a hurry, I want to go in every cycle RH, just put 0, and it will work. It will call it in every iteration. And just to also be clear, it will always call RH in the first cycle and at the end. So even if it's changing the atmosphere and it's not changing enough the temperature, in the last cycle, when you said, when the code says, I got this profile, this is the best I get, it will call RH, it will reevaluate the departure coefficients, and you will get the final solution from RH. Okay. Good. So then tomorrow, because I think we are going faster than I was expected. So tomorrow we will start from here, we will play a bit, and we will check the difference between trying to improve the solution for calcium and then check that it's also valid for iron. So before leaving, there any question? I think now we are getting a bit more on track and it's getting a bit funnier, but is there something that I said and you said, oh, I didn't got that part, like that? No, about the atoms, about other things? No? Okay. Then how was it? Good? Okay. Okay. So then shall we close for today? Yeah. Rebecca, is it fine or do you want to have some? Okay. Okay. Good. Thank you. Hi. Yeah. I forgot to say that. I write? Yeah. No, I want to write in the control file. Yes, 1 second. So, sorry. I forgot. Let me tell you one thing in case you want to test things at home. Sorry, yeah, I'm out of. Did it work now? Yeah, okay. So then, sorry, I forgot that there's one option in the control file here. So I forgot about that. So yes, sorry, sorry. So as we are always trying to improve the speed in design because we know Non-LTE is much slower. We assume that in general, you will only be interested on getting the final atmosphere and the final profile. But I think in one of the plots, in fact, that it comes later, I'm plotting the different atmospheres one by one. So then if you want to get all the atmospheres, all the profiles for each cycle, you need to put one here. In final evaluation profile, you put one, and then the code will write, if you have 5 iterations, you will have 5 profiles and 5 atmospheres. So -1, -2, -3, -4, -5. If you put 0, then you will only get -5. Okay, sorry about that. So then if you plan to do tests today or tomorrow morning, and you want to compare how the code is evolving from one cycle to the other, just put 1 there, and then you will get in your local folder all this cycle files, or profile and atmosphere. And I don't know, but it's not writing errors. So I send a mail to Basilio, but we are not getting errors. It should be there, but I don't know why this version, for some reason, is not writing them. But as soon as I get a new version, that is not going to be this week, I will just send you an email, and then you can run the same examples, and you will get for each cycle the profile, the atmosphere, and the error. So right now it's not writing the error, but it should be there. It's like 0. So I think there's some bug. Okay. So fine. Yeah. Okay. Good. Yeah.
Notice that in the RH keyword input, there's a option said the radiation is treated in field free, and the default is no stocks. Could you explain the different treatment of the field free, and does that mean that during the inversion, RH doesn't care about the magnetic field, or how does it treat the magnetic field?
Yeah, so I think the option that it has is Stokes, right? Yes. So I think this is probably Han will explain it. Han, I think he will explain it and tomorrow. But essentially, I think is so now Stokes will be that it's only intensity. Full Stokes, I think it's solving for all rays the right transfer solution, but I think in general it's too much. And then field free, I think it's probably the best scenario for us, but field free means so I think, I don't know if you have seen this cycle of with the radiative transfer equation here and then connecting to the statistical equilibrium equations and then going back. So I think in this case, the magnetic field is not included in the statistical equilibrium equations, but is included in the radiative transfer equation. So feel free, as a handset, probably for these lines it's fine. And it's much faster, much faster.
Okay, so it means when we calculate the deviation of
it's included when solving the radiative transfer equation, but not when computing the populations. So the magnetic field will not affect to the populations and of the levels, but it will affect the radiative transfer equation that somehow will interact with the statistical equilibrium equation. Okay. Okay, okay. So let's do one thing. So tomorrow, because we have time, if you want, I can quickly check. So I can quickly show you and explain you some of the keywords from our age. So we can do it tomorrow. I think Han will explain our age, so I didn't want to enter here. But at least if you want, I can just explain a bit about this tomorrow, because I think we are with a good pace. So I can quickly explain you that. So more questions now that we are here? No? Okay, so then just that, keep in mind that if you want to have all the files for each inversion cycle, just put 1 here. And if not, just put 0, and then you will get the final one. So then, and then, sorry, and then if you are running 2 cycles now playing, and then you move to 3, you are keeping 0, then it means that the -2 will be from previous test. So sometimes if you are playing with cycles, or either put 1 here and you know that you are always overwriting them, or just remove the profiles that you have and the atmospheres that you have, and then run the inversion.